Hello and welcome. I'm so glad you're here tonight. Whether you're settling into bed after a long day or simply seeking a peaceful moment to learn something extraordinary, you've arrived at exactly the right place. Tonight, we're going to explore one of the most remarkable discoveries in the history of astronomy. A visitor so ancient, so mysterious that it has fundamentally changed how we understand our place in the cosmos. On the night of July 1st, 2025, in the high desert of Chile, a telescope scanned the heavens as it did every night, searching for asteroids that might pose a threat to Earth. But what it found instead was something no one expected: a faint point of light moving impossibly fast on a trajectory that defied everything we know about objects in our solar system. This wasn't an asteroid. This wasn't a comet from our cosmic neighborhood. This was something that had traveled for billions of years through the vast darkness between the stars, something that had witnessed the birth and death of entire stellar systems, something that carried within it the chemical secrets of worlds we will never see. And on that warm summer night in Chile, humanity detected only the third confirmed interstellar object ever to pass through our solar system, 3IATLAS. If you're enjoying this journey through the cosmos, I'd be grateful if you take a moment to like this video and subscribe to the channel. It truly helps us continue creating these bedtime science stories that blend rigorous research with the peaceful contemplation that makes learning so deeply satisfying. And now, let's begin our exploration of the ancient wanderer that changed everything. To understand why 3IATLAS is so extraordinary, we need to first grasp what makes an object interstellar. Every night when you look up at the sky, nearly everything you see belongs to our solar system or our galaxy. The planets, the asteroids, the comets, they're all gravitationally bound to our sun, orbiting in predictable paths that have been traced for millions or billions of years. Even comets from the distant Oort cloud, that spherical shell of icy bodies extending nearly halfway to the nearest star, are still part of our sun's family. They might take thousands of years to complete a single orbit, but they always return. Interstellar objects are fundamentally different. They're not bound by our sun's gravity. They're passing through visitors from elsewhere, and the mathematics of their trajectories tell an unmistakable story. When astronomers calculate an object's orbital path, they look at something called eccentricity. An eccentricity of 0 means a perfect circle. An eccentricity just under 1 means an elongated ellipse, still a closed orbit. But an eccentricity greater than 1, that's a hyperbola, that's an open curve. That's an object moving so fast that it will never return. And 3IATLAS has an eccentricity that places it firmly in hyperbolic territory, confirming beyond doubt that it originated somewhere beyond our solar system, in the vast expanse of interstellar space. But here's what makes this discovery so profound. We've only confirmed 3 such visitors in all of human history. 3 objects out of countless billions that might be drifting through the galaxy that we've been fortunate enough to detect as they pass through our small corner of the universe. The first was One-Eye Oumuamua, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Its name means a messenger from afar arriving first in Hawaiian, and messenger it certainly was. Oumuamua was bizarre, a tumbling, elongated object with no visible tail, no coma of gas and dust, behaving more like an asteroid than a comet, yet showing unexpected acceleration that suggested something was pushing it. For 80 days, astronomers around the world studied it intensely, scrambling to gather every possible piece of data before it vanished back into the darkness. And then it was gone, leaving us with more questions than answers. Was it a rock? A chunk of nitrogen ice? Something else entirely? The debate continues to this day. Then came 2I Borisov in August 2019, discovered by amateur astronomer Gennady Borisov from his observatory in Crimea. Unlike the enigmatic Oumuamua, Borisov looked reassuringly familiar, a proper comet with a bright coma and a graceful tail outgassing as it approached the sun. It was like encountering a stranger who spoke your language. Scientists had 9 months to study it, watching as it brightened, observing its composition, comparing it to comets from our own Oort cloud. And while it had some unusual characteristics, a surprisingly high polarization evidence of nuclear fragmentation, it was recognizably comet-like. It felt in a strange way like home. And then on that July night in 2025 came 3IATLAS, the third confirmed interstellar visitor. But this one was different from both its predecessors in ways that would only become clear as the observations accumulated. This one would prove to be something truly extraordinary. The ATLAS telescope that discovered it, the Asteroid Terrestrial Impact Blast Alert System, sits in the crystalline air of Rio Hurtado, Chile, part of NASA's Planetary Defense Network. These telescopes work tirelessly night after night, scanning the sky for anything that might threaten Earth. But planetary defense serves a dual purpose in searching for dangerous near-Earth objects. These systems also sweep up discoveries of incredible scientific value. And 3IATLAS was exactly such a discovery. When the first observations came in, astronomers immediately noticed something unusual. The object was fast, very fast. It was traveling at approximately 137,000 miles per hour, more than 220,000 kilometers per hour relative to the sun. That's roughly 160 times faster than a rifle bullet. It's the kind of speed that immediately triggers alarm bells in the minds of astronomers who study orbital mechanics. Nothing gravitationally bound to our sun moves that quickly at that distance from our star. But speed alone doesn't confirm interstellar origin. You need the full picture position, velocity, trajectory. Within hours of the initial detection, observatories around the world began tracking 3IATLAS. The Minor Planet Center received observation reports from telescopes in Chile, California, Hawaii. Each observation refined the orbit calculation. And with each refinement, one thing became increasingly certain: this object had come from outside our solar system. Even more remarkable, astronomers found pre-discovery images. This is one of the beautiful aspects of modern astronomy. So many telescopes are constantly photographing the sky that when something interesting is found, you can go back through the archives and find earlier images of the same object before anyone knew it was there. For 3IATLAS, these pre-discovery observations extended back to June 14, 2025, allowing astronomers to construct a more complete picture of its trajectory. Now, here's where the story becomes truly extraordinary. As data accumulated and sophisticated analysis began, researchers at Harvard University, led by graduate student Shokruz Kakarov and Professor Abraham Loeb, undertook an ambitious project. They wanted to know, where did 3IATLAS come from? Not just which direction that was already known, but which stellar population. How old might it be? What region of the galaxy had been its home for billions of years? To answer these questions, they used the gravitational model of our Milky Way galaxy to trace 3IATLAS's trajectory backward through time. Imagine running a film in reverse, watching as this ancient traveler retraced its steps through space, moving backward through the galactic disk, its path shaped by the gravity of countless stars. The calculations required accounting for the rotation of the galaxy, the gravitational potential of dark matter, the vertical structure of the galactic disk. It was computational detective work of the highest order, and what they found astonished the astronomical community. The 3IATLAS is ancient. Based on its vertical excursion from the galactic plane, essentially how far it ventures above and below the flat disk of the Milky Way, the Bayesian statistical analysis suggested a median age of 4.6 billion years. Let that number settle into your mind for a moment. 4.6 billion years. That's approximately the same age as our sun, the same age as Earth. 3IATLAS has been wandering through interstellar space since the epoch when our own solar system was forming from a collapsing cloud of gas and dust. To put this in perspective, 1 Oumuamua appears to be only about 1 billion years old. originating from the thin disk of the Milky Way, where new stars are still actively forming. It's a youngster, cosmically speaking. 2I Borisov falls somewhere in between, at approximately 1.7 billion years also from the thin disk. But 3IATLAS comes from what astronomers call the thick disk. Now, our galaxy isn't a simple flat structure. It has layers like a cosmic layer cake. The thin disk where our sun resides is relatively young, about 400 light-years thick, populated by stars that are generally younger than about 5 billion years. These are stars formed from gas that has been enriched with heavy elements from previous generations of stars. But above and below the thin disk lies the thick disk, an older, puffier structure, roughly 3,000 light-years thick, populated by stars that formed in the violent early epochs of our galaxy's history, when giant clouds of gas collided and merged, when stellar birth rates were far higher than today, when the galaxy was still, in many ways, finding its form. Stars in the thick disk are older, with lower metallicity, meaning they contain fewer heavy elements because they formed closer to the beginning of cosmic time, before many generations of stars had lived, died, and scattered their enriched ashes through space. And it's from this ancient stellar population, from this thick disk component of our galaxy, that 3IATLAS appears to have originated. It's a relic, a fossil, a sample of material from planetary systems that formed when our galaxy was young. Think about what this means. When 3IATLAS was born, when it formed as a small icy body in some distant planetary system around some unknown star, Earth didn't exist. Our sun was just beginning to ignite hydrogen fusion in its core. The rocky planets were still coalescing from the protoplanetary disk. Life, if it existed anywhere in the universe, was in its most primitive form. And already 3IATLAS was being ejected from its home system, cast out into the interstellar darkness, to begin a journey that would last billions of years. But 3IATLAS isn't just old, it's also large. Observations from the Hubble Space Telescope in August 2025 allowed astronomers to place constraints on its size. The nucleus is estimated to be at least 1,400 feet across, that's about 440 meters, and possibly as large as 3.5 miles or 5.6 kilometers in diameter. To give you a sense of scale, 1I Oumuamua was approximately 100 meters across. 2I Borisov was roughly 400 meters to 1 kilometer. 3IATLAS dwarfs both of them. It's larger by 3 to 6 orders of magnitude in volume, depending on the exact size estimates. This isn't just a pebble from another star system. This is a mountain, a world unto itself. And mass follows from size. Based on the estimated dimensions and assuming a density typical of cometary nuclei, think dirty snowballs, mixtures of ice and rock with lots of empty space. 3IATLAS likely has a minimum mass of around 33 billion tons. That's 33 followed by 9 zeros in kilograms. It's enough mass to fundamentally alter the dynamics of any small object it encountered. Enough mass to have survived 6 billion years of cosmic radiation, micrometeorite impacts, and gravitational encounters with other objects in interstellar space. Now, you might be wondering, why is this discovery considered to have changed everything? After all, we've seen interstellar objects before. We knew they existed. What makes 3IATLAS so transformative? The answer lies in what it represents. For the first time in human history, we have access, however fleeting, to material from a planetary system that formed in the early history of our galaxy. We can study its chemistry, we can observe its physical properties, we can measure its composition. And all of this gives us a window into conditions that existed in the Milky Way billions of years ago in regions of space we will never visit around stars that may no longer even exist. It's as if someone had sent us a message in a bottle launched 4.6 billion years ago that only now washes up on our cosmic shore. Except this bottle is 5 kilometers across and traveling at 137,000 miles per hour. And the message it carries isn't written in words. It's written in chemistry, in physics, in the very atoms and molecules that comprise this ancient wanderer. Astronomy has traditionally been a science of remote observation. We look at distant objects through telescopes. We analyze their light. We build models and theories. But we rarely get to touch the material itself. Meteorites give us samples from our own solar system. Moon rocks give us pieces of our celestial neighbor. But 3IATLAS, this is something different. This is material from beyond. And even though we can't physically retrieve it, it's moving far too fast, and it will never return. The very fact that we can observe it, study it, analyze its composition, represents a fundamental shift in our capability to understand the universe. Before One-Eye Oumuamua's discovery in 2017, we had no direct evidence that objects from other star systems could reach our solar system. It was theoretically predicted, of course. Models of planetary system formation suggested that countless bodies should be ejected during the chaotic early phases of planet building. Gravitational interactions with giant planets should fling rocky and icy bodies into interstellar space at rates that would populate the galaxy with trillions upon trillions of rogue asteroids and comets. But theory and observation are different things. And until 2017, it remained just theory. Now, in less than a decade, we've confirmed 3 visitors. 3 data points may not seem like much, but in astronomy, 3 is infinitely more than 0. 3 allows you to begin asking questions about populations, about distributions, about diversity. And what these 3 objects have shown us is that interstellar visitors are remarkably diverse. They come in different sizes from different stellar populations, with different ages exhibiting different behaviors. They're not all the same. And that diversity tells us something profound about the galaxy we inhabit. Each of these objects carries information. One-Eye Oumuamua, with its puzzling acceleration and lack of cometary activity, taught us that interstellar objects can be surprising, that they don't always fit our preconceptions. 3I Borisov, with its familiar cometary appearance but unusual internal composition, showed us that even when something looks normal, it can harbor significant differences when examined closely. And now, 3IATLAS, with its ancient origin and substantial size, is teaching us that the galaxy has been manufacturing and ejecting planetary building blocks for billions of years, creating a vast population of nomadic objects that drift forever between the stars. Think about the implications. If 3IATLAS formed 6 billion years ago and was ejected from its home system shortly thereafter, it has been traveling through the galaxy for essentially the entire history of our solar system. While Earth was forming, while the first oceans condensed, while the first simple life emerged, while that life evolved through countless forms, while continents shifted and ice ages came and went, while our ancestors emerged and built civilizations through all of that immense span of time. Atlas was out there moving through the darkness, a silent witness to the galaxy's evolution. It has crossed through spiral arms of the Milky Way. It has passed near countless other stars, though likely never close enough to be captured by any of them. It has felt the subtle tug of dark matter halos and the combined gravitational pull of billions of stars. It has survived encounters with molecular clouds, with regions of active star formation, with the violent shocks of supernova explosions propagating through the interstellar medium. And somehow, through all of that, it has remained intact, battered certainly, coated with a crust of radiation-processed material, undoubtedly. But fundamentally the same object that was ejected so long ago. And now, by pure chance, its trajectory has brought it through our solar system. Not close to Earth, we'll discuss the details of its passage in a later section, but close enough for our instruments to detect it, to study it, to learn from it. The probability of this happening of an ancient interstellar object, passing within detection range during the brief window of human technological civilization, is remarkably small. We're extraordinarily fortunate, and that fortune has given us an unprecedented opportunity. So, as you drift towards sleep tonight, consider this: somewhere in the vast darkness between the stars, objects like 3IATLAS are countless. Every planetary system in the galaxy likely ejects similar bodies during its formation and evolution. Astronomers estimate that there might be trillions of such objects in the Milky Way alone. Most will never pass close to any star again. They'll wander forever in the deep cold of interstellar space, frozen relics of worlds that once were or might have been. But a few by chance will cross through stellar systems like ours, and an even smaller fraction of those will be detected. 3IATLAS is one of the lucky ones, and so are we. For a brief moment in cosmic time, our trajectories have intersected. An ancient wanderer from the thick disk of the galaxy has passed through the realm of a young star in the thin disk. And that intersection has given us the precious gift of knowledge about where we came from, about how planetary systems form and evolve, about the chemical diversity of the galaxy, about the deep history of the Milky Way itself. We stand at the beginning of a new era in astronomy, an era where interstellar visitors are not myths or theories but observed realities, an era where we can study material from other star systems without leaving our own, an era where the question is no longer, do interstellar objects exist, but rather, what can they teach us? And 3IATLAS, this ancient mountain of ice and rock from 4.6 billion years ago, is teaching us volumes. But its story doesn't end with discovery and age determination. To truly understand 3IATLAS, we need to follow its journey not just backward through time to its origin, but forward through space as it traverses our solar system. We need to understand the physics of its motion, the chemistry of its composition, the observations that have been made and continue to be made. We need to place it in context with its interstellar siblings, Oumuamua and Borisov, and understand what makes each unique. Most importantly, we need to consider what this discovery means for the future of astronomy and our understanding of our place in the universe. Because, make no mistake, 3IATLAS has changed everything, and its legacy will shape astronomical research for decades to come. So, let's continue this journey together, tracing the path of this ancient visitor through both time and space, and discovering what secrets it carries from the distant past of our galaxy. Imagine, if you can, a journey so vast that it spans nearly half the age of the universe. A journey not measured in miles or kilometers, but in light years, thousands upon thousands of them. A journey through regions of space so empty that you might travel for centuries without encountering anything larger than a grain of dust. This is the journey of 3IATLAS, and understanding it requires us to think about motion, time, and space in ways that challenge our everyday intuition. When we left our story, 3IATLAS had just been discovered, and astronomers had determined that it was approximately 4.6 billion years old, originating from the thick disk of the Milky Way galaxy. But what does that actually mean? Where has this object been? What has it experienced? And how do we even begin to trace a trajectory that stretches back through such incomprehensible spans of time? Let's start with the structure of our galaxy itself, because understanding where 3IATLAS comes from requires understanding the cosmic landscape it has traversed. The Milky Way isn't simply a flat disk of stars, though that's often how we picture it in illustrations. It's a complex, layered structure with distinct components, each with its own population of stars, its own characteristic motions, its own history. At the very center lies the galactic bulge, a roughly spherical concentration of old stars, densely packed, many of them, formed in the first billion years after the galaxy came into being. Moving outward, we encounter the thin disk. This is where our sun resides, about 26,000 light years from the galactic center. The thin disk is relatively young in astronomical terms, containing stars generally less than about 10 billion years old. with an average age closer to 5 billion years. It's thin in the vertical direction, only about 400 light-years from top to bottom, but it extends radially for tens of thousands of light-years. This is where most of the star formation in our galaxy happens today. This is where you find bright, hot young stars, molecular clouds rich in heavy elements, planetary systems actively forming. But surrounding and interpenetrating the thin disk is the thick disk. And this is where 3IATLAS's story begins. The thick disk is older, puffier, extending about 3,000 light-years in the vertical direction. Its stars formed earlier in galactic history, when the Milky Way was younger, more chaotic, more violent. These are stars with lower metallicity, meaning they contain fewer heavy elements, like carbon, oxygen, iron elements that are manufactured in the cores of stars and scattered through space when those stars die. Lower metallicity tells us these stars formed from gas that hadn't been enriched by many previous generations of stellar death and rebirth. The thick disk stars also move differently. Stars in the thin disk, including our Sun, orbit the galactic center in fairly circular paths, all moving in roughly the same direction, like cars on a highway. But thick disk stars have more eccentric orbits, more random motions, larger velocities perpendicular to the galactic plane. They bob up and down as they orbit, ranging far above and below the thin disk, like flotsam rising and falling on ocean waves. And it's this vertical motion, this excursion from the galactic midplane, that allowed astronomers to determine where 3IATLAS came from. When Kakarov and Loeb at Harvard ran their simulations tracing 3IATLAS's path backward through time, using the gravitational model of the Milky Way, they watched how far above and below the galactic plane the object traveled over billions of years. Objects from the thin disk stay close to the midplane, rarely venturing more than a few hundred light-years up or down. But objects from the thick disk range much farther, their vertical excursions extending to thousands of light-years. 3IATLAS shows exactly this signature. Over the past 5 billion years, roughly, its trajectory has taken it far from the galactic plane, up into the halo regions, and back down in a pattern consistent with thick disk kinematics. The Bayesian statistical analysis, which combined these orbital calculations with theoretical models of how stellar velocities change with age, pointed strongly toward an origin in this ancient thick disk population. The median age came out to 6 billion years, with a 68% confidence interval ranging from about 3.8 to 5.3 billion years. In other words, astronomers can say with reasonable certainty that 3IATLAS is older than our Sun, older than Earth, a genuine relic from the early epochs of our galaxy. But here's something that many people misunderstand about interstellar objects: they're not moving through some static, unchanging void. Space is dynamic. The galaxy rotates, stars move, gravitational fields shift. And over billions of years, these effects accumulate in profound ways. Our Sun, for example, orbits the galactic center at a velocity of about 230 kilometers per second. That's roughly 14,000 miles per hour. It takes approximately 225 million years to complete one orbit, a period sometimes called a galactic year. Since the Sun formed 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. During that time, it has passed through spiral arms regions of higher stellar density, where star formation is triggered by compression of molecular clouds. It has encountered giant molecular cloud structures containing millions of times the mass of the Sun. It has been gravitationally perturbed, though very gently, by countless stellar encounters. 3IATLAS has experienced all of this as well, but from a different starting point with a different velocity on a different path. When it was ejected from its home system, presumably somewhere in the thick disk, though we'll never know exactly where, it inherited some velocity from its parent star's motion, plus whatever additional kick it received from the ejection event itself. And from that moment on, it has been moving through the galaxy, its path shaped by the collective gravity of hundreds of billions of stars, plus the dark matter halo that surrounds and permeates the Milky Way. Now, let's talk about the speed of 3IATLAS, because this is where the numbers become truly staggering. When it was discovered on July 1st, 2025, within the orbit of Jupiter, at a distance of about 410 million miles from the Sun, it was traveling at approximately 137,000 miles per hour, or 221,000 kilometers per hour relative to our Sun. To put this in perspective, that's about 38 miles per second, or 61 kilometers per second. It's fast enough to travel from New York to Los Angeles in less than a minute. Fast enough to circle the Earth's equator in about 18 minutes. But here's what's fascinating, that speed isn't constant. As 3IATLAS approached our Sun, the Sun's gravity pulled on it, accelerating it. By the time it reached perihelion, its closest approach to the Sun on October 30th, 2025, at a distance of about 130 million miles, it had accelerated to approximately 153,000 miles per hour, or 246,000 kilometers per hour. That's an increase of 16,000 miles per hour, all due to gravitational acceleration. Now, as it moves away from the Sun, heading back out toward interstellar space, it's slowing down, again fighting against the Sun's gravitational pull. Eventually, when it's far enough away that the Sun's influence becomes negligible, it will settle back to approximately the same speed it had when it entered the solar system. This is one of the beautiful conservation laws of physics. Objects moving under gravity alone conserve their total energy. The sum of kinetic energy of motion, and potential energy of position in a gravitational field remains constant. How does this compare to other objects in our cosmic neighborhood? Consider the fastest human-made objects. The Parker Solar Probe, which holds the record for the fastest spacecraft ever built, reaches speeds of about 430,000 miles per hour when it whips around the Sun at perihelion. That's faster than 3IATLAS, but only because Parker Solar Probe starts from a bound orbit and falls deep into the Sun's gravity well. Starting from interstellar space, 3IATLAS's velocity is actually quite remarkable. Compare it to the Voyager spacecraft, humanity's most distant ambassadors. Voyager 1, launched in 1977, is now outside the solar system, traveling at about 38,000 miles per hour relative to the Sun. It's the fastest object we've ever sent into interstellar space. 3IATLAS is moving about 3.6 times faster than Voyager 1. If Voyager 1 takes about 70,000 years to travel 1 light year at its current speed, 3IATLAS would cover the same distance in roughly 19,000 years. Still incredibly slow by cosmic standards, light itself travels a light year in, well, 1 year, but remarkably fast for a chunk of rock and ice. Think about what this means for 3IATLAS's journey. Over 6 billion years, traveling at an average velocity of roughly 60 kilometers per second, relative to the local standard of rest, the average motion of stars in the solar neighborhood, it has covered an enormous distance. Light traveling for 4.6 billion years would cover 4.6 billion light years. 3IATLAS moving at about 0.002%, the speed of light has covered roughly 900,000 light years. That's enough to traverse the entire Milky Way disk multiple times. It's enough to travel from our galaxy to the Andromeda Galaxy, our nearest large galactic neighbor, and cover about a third of the distance. But, of course, it hasn't traveled in a straight line. Gravity doesn't allow that. Every star it has passed near every molecular cloud, every spiral arm has pulled on it, deflecting its path slightly. The cumulative effect of billions of years of these subtle deflections has been to send 3IATLAS on a wandering path through the galaxy, up and down through the thick disk, perhaps even venturing into the halo regions, at times a cosmic pinball bouncing off invisible gravitational bumpers. And during all this time, what has it witnessed? This is where the story becomes almost poetic. though we're firmly grounded in physical fact. When 3IATLAS was young, when it had just been ejected from its home system, the Milky Way looked different than it does today. Star formation rates were likely higher. The galaxy was more gas-rich, less heavy element-enriched. The thick disk was still actively forming, with giant molecular clouds colliding and merging, triggering bursts of star formation. 3IATLAS has passed near, though probably not very close to countless stars over its lifetime. Most of these encounters would have been distant thousands of astronomical units away, at minimum barely perceptible as gravitational tugs. But some might have been closer. It might have passed within a few light years of massive stars destined to explode as supernovae. It might have drifted through the outer reaches of planetary systems, too distant to be captured, but close enough to feel the pull of distant giant planets. It has certainly passed through molecular clouds, though, likely in their outer, less dense regions. These clouds, the stellar nurseries where new stars form, can span hundreds of light years and contain thousands or millions of solar masses of gas and dust. Passing through one would have exposed 3IATLAS to collisions with gas molecules, with dust grains slowly eroding its surface, sputtering away atoms, perhaps depositing a thin patina of interstellar material. It has survived exposure to cosmic rays' high-energy particles, mostly protons that zip through interstellar space at nearly the speed of light. Over billions of years, this radiation has processed the surface layers of 3IATLAS, breaking chemical bonds, creating new compounds, darkening the ices, creating a radiation-hardened crust. Scientists estimate that objects in interstellar space develop such crusts to depths of perhaps a meter or more, effectively insulating the pristine interior from further radiation damage. It has felt the subtle pressure of starlight from distant suns. Though incredibly weak, the radiation pressure from a star at a distance of 1 light year is almost negligible over billions of years and countless stellar encounters. Even this faint pressure adds up, contributing minutely to 3IATLAS's path through the galaxy. And here's something truly remarkable to consider during its journey. 3IATLAS has been essentially frozen. In the vast emptiness of interstellar space, far from any star temperatures, are incredibly cold, only a few degrees above absolute zero, perhaps 2.7 Kelvin. The temperature of the cosmic microwave background radiation left over from the Big Bang. At these temperatures, chemistry essentially stops. Volatiles like water, carbon dioxide, methane, ammonia, all frozen solid. No sublimation, no activity, no change. 3IATLAS has been in a state of near-perfect preservation, a time capsule carrying the chemical signature of its formation environment, until July 2025, when it entered the inner solar system and began to feel the sun's warmth. For the first time in potentially billions of years, the surface temperature rose above the point where ices begin to sublimate. Water molecules freed from the solid matrix began to escape into space, carrying dust grains, with them creating the characteristic coma and tail that we associate with comets. 3IATLAS woke up in a sense after an unimaginably long sleep. But let's step back and consider the broader picture, because there's a common misconception that needs addressing. Many people, when they hear about interstellar objects, imagine them as incredibly rare, one-of-a-kind phenomena. The reality is quite different. Based on the discovery rate of interstellar objects and accounting for the limited survey coverage of the sky, astronomers estimate that there might be one interstellar object passing within the orbit of Neptune at any given time. One. Right now, as you listen to this, there's likely an interstellar visitor somewhere in the outer solar system, undetected on its way through. And in the galaxy as a whole, the numbers become almost incomprehensible. Current estimates suggest there might be trillions, 10 to the 13th power, or 10,000 interstellar objects wandering through the Milky Way at any moment. That's more than the number of stars in the galaxy. These objects outnumber stars, but they're so small and dark and spread out over such vast distances that they're nearly impossible to detect unless they happen to pass very close to us. This means that space is not empty. The regions between the stars contain a vast invisible population of rogue worlds, icy bodies, rocky asteroids, perhaps even planets ejected from their home systems, all silently drifting through the darkness. Some were ejected recently on timescales of millions of years. Others, like 3IATLAS, have been wandering for billions of years, nearly as long as the galaxy has existed in its current form. And here's something that brings us full circle to the question of where 3IATLAS has been. Most of these objects will never be captured by another star. The distances between stars are simply too vast, the gravitational reach of any single star too small. 3IATLAS's passage through our solar system is unusual precisely because it happened across our path during the brief moment of human technological civilization. In all its 4.6 billion years of wandering, it has likely never before passed this close to a star that harbored intelligent observers capable of detecting it. Think about the timing. If 3IATLAS had arrived 100 million years earlier, it would have passed through a solar system where Earth was dominated by dinosaurs. No human would have seen it. No telescope would have captured its image. It would have come and gone, unnoticed, unrecorded. If it had arrived 100 million years in the future, who knows what civilization, if any, might observe it. The fact that it arrived now during this particular century, during the age of space telescopes and computational astrophysics, is pure coincidence. But it's a coincidence that has given us an extraordinary gift. Because in studying 3IATLAS, we're not just learning about one object. We're learning about the processes that govern planetary system formation across the entire galaxy. We're learning about how objects are ejected, how they survive in interstellar space, how diverse their compositions and origins can be. We're learning about the thick disk of our galaxy, that ancient stellar population that formed when the Milky Way was young. We're learning about the history of star formation, about galactic dynamics, about the chemical evolution of the cosmos itself. Every data point we gather from 3IATLAS, every spectrum, every image, every measurement of its trajectory and its activity adds to this body of knowledge. And as we'll explore in the next section, the chemistry of 3IATLAS holds particular surprises, clues to formation conditions in planetary systems, very different from our own, perhaps even hints about the ingredients necessary for life itself. The ancient journey of this cosmic wanderer has brought it to our doorstep at precisely the moment we're ready to learn from it. And the lessons it carries from the deep past of our galaxy are only beginning to unfold. When astronomers first analyzed the light coming from 3IATLAS, splitting it into its component wavelengths through spectroscopy, they discovered something that sent ripples of excitement through the scientific community. The chemical signature was unlike anything they had seen before in comets from our own solar system. Hidden within those spectral lines was evidence of a planetary system profoundly different from our own, a world that formed under conditions we're only beginning to understand. And perhaps most intriguingly, this ancient visitor carried within it the very building blocks that life requires. Chemistry at its heart is the story of atoms coming together, breaking apart, and rearranging themselves into new configurations. And in the vast cold of space, chemistry tells us where objects formed, what temperatures they experienced, what raw materials were available in their birth environment. Every molecule is a clue, every atomic ratio a fingerprint pointing back to origin. So, when we examine the chemistry of an interstellar object, we're essentially reading its autobiography, written in the language of carbon, oxygen, hydrogen, and nitrogen. The first major discovery came from observations made in October 2025 as 3IATLAS approached its closest point to the Sun. Multiple observatories detected emissions at specific wavelengths that indicated the presence of various molecules being released as the comet's ice is heated and sublimated. And one particular ratio immediately caught astronomers' attention: The ratio of methanol to hydrogen cyanide was anomalously high, significantly higher than what's typically seen in comets from our own solar system. Now, let's unpack what this means, because this single finding opens a window into an alien world. Methanol chemical formula. CH3OH is a relatively simple organic molecule consisting of one carbon atom, one oxygen atom, and four hydrogen atoms arranged in a particular configuration. It's also known as wood alcohol, and while it's toxic to humans, it's extraordinarily important in astrochemistry, because it's one of the fundamental building blocks from which more complex organic molecules can form. Hydrogen cyanide, HCN, is equally important, but represents a different chemical pathway. It consists of one hydrogen atom, one carbon atom, and one nitrogen atom bonded together in what chemists call a triple bond, one of the strongest chemical bonds that exists. HCN is present in comets and is often one of the first molecules detected because it's relatively easy to observe spectroscopically. In comets from our own solar system, whether they come from the Kuiper belt or the distant Oort cloud, the ratio of methanol to hydrogen cyanide production falls within a fairly predictable range. Scientists have studied dozens of comets over decades and established what we might call a normal baseline. But 3IATLAS doesn't fit this baseline. Its methanol to HCN ratio is much higher, suggesting either that it formed in a region unusually rich in methanol or that the chemical processes during its formation favored methanol production over HCN. One of the leading researchers studying 3IATLAS's chemistry, who has been tracking the comet's spectroscopic signatures since discovery, noted in a recent blog post that this anomalously large ratio of methanol to hydrogen cyanide production suggests a friendly nature for this interstellar visitor. Friendly? What a fascinating word choice. What he means is that high methanol content correlates with what astrobiologists call prebiotic chemistry. The kind of chemistry that could, under the right conditions, lead to the formation of amino acids, the building blocks of proteins, and eventually to life itself. But before we get too far ahead of ourselves, let's ground this in comparison. Think about 2I Borisov, that previous interstellar comet discovered in 2019. When astronomers analyzed Borisov's composition, they found it was what we call carbon chain depleted. This means it had relatively low amounts of certain carbon-based molecules, particularly diatomic carbon C2 compared to cyanide. In fact, Borisov resembled a rare class of solar system comets, sometimes called blue comets, because of their spectroscopic properties. Comets that are unusually rich in carbon monoxide relative to other carbon compounds. Borisov's composition suggested it formed in a very cold region of its home planetary system, possibly in a zone analogous to our Kuiper belt, or even farther out. The low temperatures would have allowed carbon monoxide, which has a very low freezing point, to remain gaseous longer during formation, getting incorporated into the comet's structure in higher proportions. It was pristine, ancient, relatively unprocessed. 3IATLAS appears to tell a different story. The high methanol content suggests formation in a region where carbon chemistry was more complex, where perhaps the protoplanetary disk had higher densities, or different temperature gradients where organic molecules could form more readily through reactions on the surfaces of dust grains. Methanol forms most efficiently through what chemists call hydrogenation. Reactions, the addition of hydrogen atoms to carbon monoxide molecules, and these reactions occur most effectively on cold dust grain surfaces, where molecules can stick long enough for the reaction to occur. This gives us a picture. 3IATLAS likely formed in a region of its parent protoplanetary disk, where conditions favored complex organic chemistry. Perhaps it was slightly warmer than the regions where Borisov formed, but still cold enough for these molecules to freeze out. Perhaps the disk had a higher dust-to-gas ratio, providing more surfaces for grain surface chemistry. Perhaps the parent star's radiation environment, Was different driving different photochemical reactions? We can't know for certain. The system where 3IATLAS formed probably doesn't even exist anymore, at least not in its original form, but the chemistry gives us clues. Now, here's where it gets really interesting from an astrobiology perspective. Methanol is not just a random molecule. It's a key intermediate in what chemists call the formaldehyde pathway to forming more complex organics. In laboratory experiments simulating interstellar and cometary chemistry, methanol has been shown to be a precursor to formaldehyde, which in turn can react to form even more complex molecules like glycolaldehyde, which can ultimately lead to sugars and amino acids under the right conditions. This is the basis of the panspermia hypothesis in one of its modern forms. Not the idea that life itself travels between stars, though that's one version, but rather that the chemical building blocks of life, complex organic molecules, might be distributed throughout the galaxy by objects like 3IATLAS. When these objects were ejected from their home systems billions of years ago, they carried with them a cargo of organic chemistry, and occasionally some of them might impact young planets, delivering these molecules to worlds where they could participate in the origin of life. Could something like 3IATLAS have brought organic molecules to early Earth? It's an intriguing possibility. We know that Earth experienced what's called the Late Heavy Bombardment, roughly 3.8 to 4.1 billion years ago, a period when the inner solar system was pummeled by asteroids and comets. Some of those impactors were undoubtedly from our own solar system, but statistically a small fraction might have been interstellar visitors. If any of them carried high concentrations of methanol and other organics, they could have contributed to the primordial soup from which life eventually emerged. But let's be careful here. This is speculation, not established fact. The leap from methanol delivery to origin of life is enormous, bridging chemistry and biology across a chasm we still don't fully understand. What we can say with confidence is that 3IATLAS demonstrates that organic molecules, the kind necessary for life, as we know it, form readily in planetary systems throughout the galaxy. Life's building blocks are not unique to Earth or even to our solar system. They're a natural consequence of the chemistry that happens when clouds of gas and dust collapse to form stars and planets. Let me give you another point of comparison that illustrates just how diverse interstellar chemistry can be. Remember 1I Oumuamua? That first interstellar visitor was a puzzle precisely because it showed no cometary activity whatsoever. No coma, no tail, no detectable outgassing. For a long time, astronomers debated what it could be made of. Was it solid rock, like an asteroid? Was it made of nitrogen ice, which would sublimate without producing easily detectable gases? Was it something else entirely? One hypothesis that gained traction was that Oumuamua was essentially a shard of nitrogen ice, a fragment of a Pluto-like world from another star system. Nitrogen ice has a sublimation temperature that falls right around the range where Oumuamua was observed, and the sublimation of nitrogen produces very little visible coma. It's transparent and doesn't drag much dust. This would explain Oumuamua's strange non-gravitational acceleration. It was outgassing nitrogen, providing a tiny rocket-like push, but the nitrogen was invisible to our instruments. If this hypothesis is correct, and we may never know for certain, since Oumuamua is now far beyond observation, then we have evidence of yet another formation environment, icy worlds rich in nitrogen, low in carbon compounds probably formed in the very cold outer regions of planetary systems. Completely different chemistry from 3IATLAS. Completely different from Borisov. 3 interstellar visitors, 3 distinct chemical signatures, suggesting 3 different formation environments in 3 different planetary systems around 3 different stars. This diversity is actually one of the most important lessons 3IATLAS is teaching us. Before we detected interstellar objects, we could study comets from our own solar system and wonder, are we typical? do other planetary systems produce similar objects? Now, we know the answer is both yes and no. Yes, the basic processes are similar ice and rock accumulating in protoplanetary disks, getting incorporated into small bodies, sometimes getting ejected into interstellar space. But no. The detailed chemistry varies significantly based on the specific conditions of each system. Think about what this means for exoplanet studies. When astronomers detect planets around other stars and try to characterize their atmospheres, they often use our solar system as a reference point. But 3IATLAS reminds us that every planetary system is unique. The composition of planets depends critically on the composition of the protoplanetary disk from which they formed, which in turn depends on the metallicity of the parent star, the temperature structure of the disk, the presence of nearby massive planets that might stir things up, and countless other factors. A common misconception that 3IATLAS helps correct is the idea that all comets are basically the same dirty snowballs with roughly similar compositions. Even within our own solar system, this isn't true. Jupiter family comets, which have been perturbed by Jupiter into short-period orbits, show different compositions than long-period comets from the Oort cloud. Some comets are carbon monoxide rich, others are water rich. Some have high dust-to-gas ratios, others are mostly volatiles. And now, with interstellar comets, we're seeing even greater diversity. This diversity has profound implications for how we think about the distribution of organic molecules in the galaxy. If every planetary system produces objects with slightly different chemical signatures, then the interstellar medium, the space between the stars, is being continually enriched with a vast variety of organic compounds. Over billions of years, this creates a kind of chemical library, a reservoir of molecules that future generations of planetary systems can draw upon. Here's another fascinating detail about 3IATLAS's chemistry that emerged from the observations as it approached the sun and began to heat up. Astronomers detected not just methanol and hydrogen cyanide, but also water vapor, carbon dioxide, and traces of other molecules. The relative abundances of these molecules, how much of each was being released, told a story about the layered structure of the comet. Comets are not uniform throughout. They're more like onions with layers. The outermost layers have been processed by cosmic radiation over billions of years, as we discussed earlier, creating a radiation-hardened crust. Below this crust, you find relatively pristine ices that have been preserved since formation, and potentially different layers formed at different times or in different locations within the protoplanetary disk, giving them different compositions. As 3IATLAS warmed the most volatile molecules, those with the lowest sublimation temperatures began to escape first. Carbon monoxide and nitrogen would be among the first to go. Then, at slightly higher temperatures, carbon dioxide and water begin to sublimate more rapidly. Methanol, with its relatively low sublimation temperature for an organic molecule, would start escaping at intermediate temperatures. By observing which molecules appeared at which points in the comet's approach, astronomers could essentially peel back these layers, seeing deeper into the comet's structure. And here's something that should make you pause and marvel the molecules we're detecting from 3IATLAS: the water, the methanol, the carbon dioxide formed 4.6 billion years ago. They've been frozen locked in place for nearly the entire age of the universe's current epoch. The methanol molecules that sublimated off 3IATLAS in October 2025 are the same molecules that formed in a protoplanetary disk around an unknown star when the Milky Way was young. They're time capsules at the molecular level, preserving information about chemistry from an era we can study in no other way. This brings us to one of the most profound implications of 3IATLAS's chemistry: the universality of organic chemistry. Carbon-based molecules form readily throughout the cosmos. Because carbon has a unique property, it can form stable bonds with itself and with many other elements, creating complex structures. Silicon can do this too to some extent. which is why science fiction sometimes speculates about silicon-based life. But carbon is far more versatile, and it's abundant created in the cores of massive stars and scattered through space when those stars die. The fact that we see complex organic molecules in 3IATLAS, in 2I Borisov, in comets from our own solar system, in molecular clouds, in the atmospheres of exoplanets and meteorites, this tells us that the chemistry of life's building blocks is not a rare accident. It's a natural outcome of the physical and chemical processes that occur wherever carbon, hydrogen, oxygen, and nitrogen come together under the right conditions. And those conditions exist throughout the galaxy, around countless stars in countless planetary systems. Does this mean life is common in the universe? That's a much harder question. One that 3IATLAS can't answer directly. Having the building blocks is necessary, but not sufficient for life. You also need energy sources, liquid water, or some other solvent, the right planetary conditions, and a whole cascade of chemical reactions that we're only beginning to understand. But what 3IATLAS does tell us is that the universe is not hostile to organic chemistry. The ingredients are there scattered among the stars, delivered by objects like this ancient wanderer, as 3. Atlas continues its journey outward, leaving our solar system behind. It will eventually return to the cold of interstellar space. The ices that sublimated as it approached the sun will freeze again, if any remain. The coma will dissipate, the tail will fade, and once again, 3IATLAS will become a frozen silent ark carrying its cargo of organic molecules through the galaxy. A tiny piece of chemical history from a world long vanished. But the observations we've made, the spectra we've captured, the chemical signatures we've analyzed, these will remain with us, adding to our understanding of how chemistry shapes the cosmos, how molecules journey between stars, and how the building blocks of life are distributed throughout our galactic home. And speaking of observations, the campaign to study 3IATLAS mobilized some of the most sophisticated instruments humanity has ever built. From space telescopes, billions of dollars in value, to amateur observers with backyard equipment, all working together to capture every possible detail of this fleeting visitor. Picture this. It's July 2nd, 2025, barely 24 hours after the initial detection of 3IATLAS. Across the globe, astronomers are waking up to urgent messages, notifications pinging on their phones, emails flooding their inboxes. The Minor Planet Center has just confirmed something extraordinary, a third interstellar object passing through our solar system. And unlike Oumuamua, which was discovered as it was already leaving, this one is inbound. There's time to mobilize every available telescope. Time to coordinate observations across continents and space-based platforms. Time to gather data that might not come again for years, perhaps decades. What follows is one of the most remarkable collaborative efforts in the history of astronomy. A global campaign involving billions of dollars worth of equipment, hundreds of researchers, and even amateur astronomers in their backyards, all focused on capturing every possible detail of this ancient visitor during its brief passage through our cosmic neighborhood. The scale and coordination of this observational campaign is truly something to appreciate. So, if you're finding value in this journey through the cosmos, I'd be grateful if you'd take a moment to like this video and subscribe. Sharing these stories of scientific discovery helps us continue creating content that brings the universe a little closer to home. Now, let's dive into the remarkable efforts that have been documenting 3IATLAS. The first challenge astronomers faced was simply logistical. 3IATLAS was moving fast and would only be observable for a limited window. From discovery in early July until it passed behind the sun in late September, they had roughly 3 months of prime observation time. Then it would be lost in the sun's glare for about 2 months, from late September through November, before emerging on the other side in early December. That emergence would provide a second observation window lasting several more months. But by then, 3IATLAS would be rapidly receding, growing fainter with each passing day. 3 months might sound like a lot of time, but in astronomical terms, especially for such a unique target, it's the blink of an eye. Telescope time is precious. Major observatories are booked months or even years in advance. Getting last-minute access requires either having pre-arranged director's discretionary time for targets of opportunity or convincing other astronomers to give up their allocated slots for something more important. The discovery of 3IATLAS triggered both mechanisms simultaneously. Let's start with the crown jewel of space telescopes, the Hubble Space Telescope, launched in 1990 and still operating magnificently. 35 years later, Hubble has become humanity's most productive scientific instrument, revolutionizing virtually every field of astronomy. When 3IATLAS was discovered, the Hubble scheduling team immediately recognized the opportunity. They had experience with interstellar objects Hubble had observed both Oumuamua and 2I Borisov, and they knew this was a target that demanded priority. On July 21, 2025, just 3 weeks after discovery, Hubble turned its Wide-Field Camera 3 toward 3IATLAS. The comet was approximately 277 million miles from Earth at that point, still relatively far out, but already showing signs of activity. The images that came back were stunning. Hubble's exquisite resolution revealed a teardrop-shaped cocoon of dust surrounding the comet's nucleus. The coma, that characteristic feature of active comets, glowing softly as sunlight scattered off countless tiny particles. The Wide Field Camera 3, or WFC-3, is a remarkable instrument. Installed during the final Hubble servicing mission in 2009, it captures images across a wide range of wavelengths, from ultraviolet through visible light into the near-infrared. This panchromatic capability, the ability to see across multiple bands, simultaneously allows astronomers to tease apart different components of what they're observing. The dust in the coma scatters visible light differently than it scatters ultraviolet or infrared. And by comparing images at different wavelengths, scientists can determine the size distribution of dust particles, their composition, and how they're distributed spatially. But Hubble didn't stop with one observation. On November 30th, 2025, after 3IATLAS had passed around the far side of the Sun and re-emerged into observable space, Hubble observed it again. This second observation was crucial because it allowed astronomers to compare the comet's appearance before and after perihelion, its closest approach to the Sun. Had the activity increased? Had the nucleus fragmented, as sometimes happens when comets are heated? Was the coma brighter, denser? These before and after comparisons are invaluable for understanding how interstellar comets respond to solar heating, and whether they behave similarly to comets from our own solar system. The distance in that November observation was approximately 178 million miles from Earth, significantly closer than the July observation, and Hubble's sharp eye captured details that ground-based telescopes simply couldn't resolve. The images showed that 3IATLAS remained intact, no obvious fragmentation, but the coma had evolved its structure subtly different, reflecting the changing activity as the comet moved away from the Sun and began to cool again. While Hubble was capturing visible light portraits, another space telescope was waiting in the wings, the James Webb Space Telescope. Webb launched in 2021 and now operating flawlessly from its position at the second Lagrange point, a gravitationally stable location about 1 million miles from Earth, is optimized for infrared observations. And infrared is crucial for understanding cometary chemistry, because many molecules emit characteristic infrared signatures as they vibrate and rotate, heated by solar radiation. Webb's observing schedule is even more precious than Hubble's, with astronomers worldwide competing fiercely for every hour of time. But the scientific value of observing an interstellar object with Webb's unprecedented infrared sensitivity was undeniable. The observations conducted at multiple points during 3I-ATLAS's passage allowed researchers to detect and measure molecules that are invisible or very faint in visible light. Water vapor, carbon dioxide, methanol, carbon monoxide, each has distinctive infrared signatures, and Webb spectrographs could measure their abundances with exquisite precision. But perhaps one of the most unexpected observers was the Jupiter Icy Moons Explorer JUICE for short. This European Space Agency mission, launched in April 2023, is currently on its way to Jupiter, where it will arrive in 2031 to study Jupiter's large icy moons, Ganymede, Callisto, and Europa. It's not designed to study comets. Its instruments are optimized for a completely different scientific mission. But as JUICE cruised through interplanetary space on its complex trajectory toward the outer solar system, mission controllers realized that 3I-ATLAS would pass through JUICE's field of view in early November 2025. The opportunity was too good to pass up. Even though JUICE was designed for a different purpose, its cameras and instruments could still capture valuable data. On November 6, 2025, JUICE turned its attention toward the Interstellar visitor. The spacecraft was about 250 million miles from 3I-ATLAS, at the time not particularly close by planetary mission standards, but its instruments captured images that revealed both the glowing coma and two faint tails extending from the nucleus. Those two tails are significant. When a comet approaches the Sun, it typically develops two distinct tails pointing away from the Sun. The dust tail composed of small particles pushed away by solar radiation. Pressure is usually broad and curved, following the comet's orbital path. The ion tail, composed of ionized gas molecules, is typically narrower and straighter, blown directly away from the Sun by the solar wind, that stream of charged particles constantly flowing out from our star. The fact that JUICE could see both tails told astronomers that 3I-ATLAS was producing substantial amounts of both dust and gas, a sign of robust cometary activity. JUICE's observations were particularly valuable because they came during a critical period just after perihelion, when activity tends to peak. The spacecraft used 5 different scientific instruments, plus its navigation camera, to study the comet, capturing data that complemented what the other observatories were seeing. And here's the remarkable part: the full scientific data from JUICE's encounter is still being transmitted back to Earth. Due to the vast distances involved and the limited communication bandwidth, the complete data set won't arrive until February 2026. When it does, it will provide even more detailed information about 3I-ATLAS's composition and behavior. Now, there was one particularly challenging period when most telescopes simply couldn't observe 3I-ATLAS at all. From late September through November 2025, the comet passed behind the Sun from Earth's perspective. This is called solar conjunction, and it's a major headache for astronomers. You obviously can't point a telescope directly at the Sun. The brightness would damage sensitive instruments, not to mention overwhelm any signal from a relatively faint comet. So, for about 2 months, 3I-ATLAS was essentially invisible to Earth-based observers. But NASA had a solution: the PUNCH mission. PUNCH, which stands for Polarimeter to Unify. The Corona and Heliosphere is a constellation of 4 spacecraft launched in 2023, specifically designed to study the Sun's outer atmosphere and the solar wind. These spacecraft use coronagraphs, special telescopes that block out the Sun's bright disk with an occulting disk, allowing them to see the much fainter corona and the space immediately around the Sun. It's like creating an artificial eclipse. PUNCH wasn't designed to track comets, but researchers at the Southwest Research Institute realized it could do exactly that. They checked 3I-ATLAS's predicted trajectory and discovered that the comet would spend almost 2 full months within PUNCH's field of view, right in that blind spot where other telescopes couldn't see it. This was an unprecedented opportunity. No previous interstellar object had been continuously tracked during solar conjunction. The Punch spacecraft observed 3I-ATLAS throughout October and early November, watching as it heated to maximum temperature at perihelion, observing how the solar wind interacted with the comet's ion tail, seeing things that would have been invisible from Earth. One of the project scientists noted that this continuous observation during conjunction filled a critical gap, providing data about how the comet responded to maximum solar heating information that would have otherwise been lost. But it wasn't just the big-budget space missions capturing data. Ground-based observatories around the world joined the campaign, each contributing unique observations. The Gran Telescopio Canarias in Spain, one of the world's largest optical telescopes with a 10.4-meter mirror, obtained high-resolution spectra that revealed fine details in the comet's composition. The Keck telescopes in Hawaii, with their advanced adaptive optics systems that compensate for atmospheric turbulence, captured some of the sharpest ground-based images. The Very Large Telescope in Chile, operated by the European Southern Observatory, measured the polarization of light reflected from 3I-ATLAS's dust, providing information about particle sizes and composition. And here's something beautiful: amateur astronomers got involved too. While professionals had access to the world's largest telescopes, amateur astronomers with backyard equipment, telescopes perhaps 8 to 14 inches in diameter, could still contribute. They tracked 3I-ATLAS's position night after night, measuring its brightness, reporting when it passed near recognizable stars in the constellation Leo. These observations helped refine the orbital calculations, filled in gaps when professional observatories were busy with other projects, and democratized the discovery in a way that really matters. One amateur observer reported seeing 3I-ATLAS near the bright star Regulus in Leo, noting synchronous brightness changes. Another group documented the comet's path across the sky over several weeks, creating time-lapse animations that showed its motion against the background stars. These contributions might seem small compared to Hubble's exquisite images or Webb's detailed spectra, but they're part of the collaborative spirit that makes astronomy special: professionals and amateurs working together toward common understanding. Now, let's talk about the technical challenges these observations faced, because understanding the difficulties makes the achievements even more impressive. First, there's the brightness issue. When 3I-ATLAS was discovered in early July, it had an apparent magnitude of about 18, far too faint for the naked eye, requiring substantial telescope aperture and sensitive detectors even to see. As it approached the sun and developed its coma, it brightened somewhat, but it never became easy to observe. By December, when it made its closest approach to Earth at a distance of about 270 million kilometers, it had brightened to magnitude 10.9, observable through moderate amateur telescopes, but still challenging. Compare this to 2I Borisov, which reached magnitude 15 at its brightest, or especially to really bright comets from our own solar system that occasionally reach magnitude 0 or even negative magnitudes bright enough to see easily with the naked eye. 3I-ATLAS never became spectacular in the public eye, but that's actually typical for interstellar objects. They're small, they're far away, and they're moving quickly, making observation genuinely difficult. Second, there's the speed issue we've discussed before. 3I-ATLAS was traveling at roughly 60 kilometers per second, about 135,000 miles per hour, which means it moved noticeably against the background stars even during a single night of observation. For long exposure photography, which is necessary to gather enough light from such a faint object, this creates a technical problem. If you track the stars, the comet becomes a streak. If you track the comet, the stars become streaks. Professional observatories have sophisticated systems to track moving objects, but it requires careful planning and expert operation. Third, there's the coordination challenge. Different telescopes see different things. Optical telescopes reveal the dust coma and tail structure. Infrared telescopes measure molecular emissions and temperature. Radio telescopes can detect specific molecules through their characteristic radio emissions. Ultraviolet observations reveal the extent of the hydrogen cloud surrounding the nucleus. To get a complete picture, you need observations across the entire electromagnetic spectrum, and that requires multiple facilities working in concert, often coordinating their observations to occur simultaneously, so the data can be directly compared. The sheer logistics of coordinating this global effort are staggering. Time zones matter. When it's night in Chile, it's day in Hawaii. Weather matters. Cloudy skies can shut down ground-based observations with no warning. Telescope schedules matter. Every observatory has competing demands for time. And yet, despite all these challenges, the astronomical community pulled together, sharing data, coordinating observations, making the most of every clear night and every available instrument. Think about what this represents. In 1997, when Comet Hale-Bopp made its spectacular appearance, it was observed by professional and amateur astronomers around the world, generating tremendous public interest and valuable scientific data. But Hale-Bopp was in our sky for months, bright enough to see with the naked eye, and it came from our own solar system. The observational campaign for 3IATLAS was necessarily much more intense, much more focused, because the window was shorter and the target more challenging. And the results are still coming in. Science doesn't happen instantly. When a telescope captures an image or a spectrum, that's just raw data. It has to be processed, calibrated, analyzed. Spectra have to be compared with laboratory measurements to identify molecules. Images have to be enhanced to reveal faint features. Different data sets from different instruments have to be cross-checked for consistency. This work takes time, months, even years. Papers are still being written, data is still being analyzed, and new discoveries about 3IATLAS will continue emerging well into 2026 and beyond. One of the misconceptions that observations like these help correct is the idea that astronomy is a solitary pursuit, lone scientists gazing at the stars. The reality, at least for major discoveries, is intensely collaborative. Hundreds of people contribute to campaigns like this: telescope operators who point the instruments and manage the observations, data specialists who process the raw measurements, theorists who model what we're seeing, instrumentalists who keep the equipment running. And increasingly, this collaboration spans national boundaries. Hubble is operated by NASA and ESA jointly. JUICE is a European mission, PUNCH is American. The ground-based observatories span multiple continents. Modern astronomy is a global enterprise. As December approached and 3IATLAS made its closest pass by Earth, still a very safe distance of 1.8 astronomical units, about 270 million kilometers, observers around the world had one final chance to study it in detail before it began to fade. Telescopes across both hemispheres tracked it continuously, weather permitting, capturing photometric data, spectroscopy, everything possible. And amateur astronomers checking websites that track the positions of interesting objects pointed their own telescopes toward Leo, adding their observations to the collective effort. But studying 3IATLAS from Earth and from spacecraft orbiting near Earth tells only part of its story. To truly understand how this interstellar visitor became interstellar, in the first place, we need to explore the violent physics that can tear objects away from their home stars and fling them into the eternal darkness between worlds. Imagine a small world, perhaps no larger than a mountain, orbiting peacefully in the cold outer reaches of a young planetary system. For millions of years, it follows its predictable path, one of billions of similar objects in a disk of ice and rock surrounding a distant star. Then, in a cosmic instant, everything changes. A massive planet, perhaps 10 times the mass of Jupiter, sweeps through on an eccentric orbit, its gravity reaching out across millions of miles. The small world's trajectory bends, accelerates, and suddenly it's moving faster than it ever has before, faster than the escape velocity of its home system. In that moment, it becomes an exile condemned to wander the galaxy forever, never to return. This is how 3IATLAS likely became Interstellar, and understanding this violent physics of ejection reveals one of the most fundamental processes shaping our galaxy. The story of how objects escape their home systems is really a story about gravity energy and the chaotic dynamics of planetary formation. So, if these cosmic mechanics fascinate you, I'd truly appreciate if you would like this video and subscribe to the channel. Your support helps us explore these profound questions about how the universe works. Now, let's dive into the physics that creates interstellar wanderers. To understand how 3IATLAS became interstellar, we first need to grasp a deceptively simple concept: escape velocity. Every massive object creates a gravitational well, a region of space where other objects are pulled toward it. To completely escape this gravitational influence to break free and never return, you need to be moving faster than a specific speed called the escape velocity. This isn't just any velocity. It's the exact speed where your kinetic energy, the energy of motion, equals the gravitational potential energy binding you to that object. For Earth, the escape velocity at the surface is about 11.2 kilometers per second, or roughly 25,000 miles per hour. Rockets launching satellites into deep space need to reach this speed to leave Earth's gravitational influence. For the Sun, measured from Earth's orbital distance, the escape velocity is about 42 kilometers per second. This is why interplanetary spacecraft, even after escaping Earth, are still bound to the Sun. They're not moving fast enough to escape the solar system entirely unless they get a gravity assist from a planet. Now here's the critical insight. When 3IATLAS was discovered traveling at 137,000 miles per hour relative to the Sun, it was moving well above the solar escape velocity at its location. This immediately told astronomers it wasn't bound to our Sun. But more importantly, when they traced its trajectory backward, calculating where it had come from, they found that it had entered our solar system already moving at interstellar velocities. This means that whatever ejection event sent it into interstellar space happened billions of years ago in a completely different stellar system. So, what kind of event can accelerate a comet-sized object to such speeds? There are three primary mechanisms, and each tells us something different about planetary system evolution. The first and probably most common mechanism is gravitational ejection by giant planets. This process, called a gravitational slingshot or gravity assist, is actually something we use intentionally with spacecraft. When Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune in succession, it used each planet's gravity to increase its velocity. The spacecraft fell toward each planet, accelerated, then whipped around behind the planet and was flung outward, stealing a tiny bit of the planet's orbital momentum in the process. Each encounter added speed, and by the time Voyager 2 left Neptune, it had enough velocity to escape the solar system entirely. The same physics works with small bodies and planetary systems, but on a much grander and more chaotic scale. During the early epochs of planetary system formation, roughly the first 100 million years, things are messy. You have giant protoplanets still migrating through the disk of leftover material, their gravitational influence stirring everything up. You have countless planetesimals, the building blocks of planets scattered throughout the system. And you have resonances regions where orbital periods create reinforcing gravitational effects that can dramatically alter trajectories. In our own solar system's history, we have strong evidence for an event called the Late Heavy Bombardment, which occurred about 3.8 to 4.1 billion years ago. Current models suggest this was triggered by orbital migration of the giant planets Jupiter, Saturn, Uranus, and Neptune. As these planets moved, their gravitational influence swept through different regions, scattering countless smaller bodies. Some fell inward toward the Sun, creating the bombardment of the inner planets whose craters we still see on the Moon. But many more were flung outward, accelerated to such high velocities that they escaped the solar system entirely. Estimates suggest that our solar system has ejected millions, possibly billions of comet-sized objects over its 4.6 billion year history. For every comet that remains in the Oort cloud, still loosely bound to the sun, but barely probably dozens or hundreds, were accelerated beyond escape velocity and are now wandering interstellar space. And if our solar system did this, every other planetary system in the galaxy presumably does the same. This creates a vast population of rogue objects, unbound wanderers, carrying with them the chemical signatures of their birth systems. 3IATLAS, originating from the thick disk and being 4.6 billion years old, was likely ejected during exactly this kind of chaotic early phase. Its parent system probably had giant planets we can't know for certain, but the physics strongly suggests it. And during the period when those giants were finding their stable orbits, 3IATLAS received a gravitational kick powerful enough to exceed escape velocity. The mathematics of this process are elegant. When a small object approaches a massive planet on a hyperbolic trajectory, meaning it's not in orbit just passing by, it can gain or lose velocity depending on the geometry of the encounter. If it approaches from ahead of the planet in its orbit, it can be accelerated forward. The maximum velocity change depends on the planet's mass and the closest approach distance. A Jupiter-mass planet can potentially add several kilometers per second to a small body's velocity. A super-Jupiter several times more massive than Jupiter can add even more. But here's something fascinating. Most ejection events don't happen with a single encounter. Computer simulations of planetary system formation show that objects typically undergo multiple gravitational interactions before being ejected. They might have close encounters with one giant planet that alters their orbit, making them cross the orbit of another giant planet, which then kicks them again, and so on. It's a pinball game played over millions of years, with each bounce either nudging the object toward escape or sending it careening through the system on a new trajectory. The second mechanism for creating interstellar objects is even more violent planetary collisions. We have good evidence that Earth experienced at least one giant impact early in its history, the collision with a Mars-sized body that created the Moon. That impact ejected enormous amounts of material, some of which coalesced into the Moon, but much of which was scattered into space at high velocity. Most of that material probably fell back or went into solar orbit, but the most energetic fragments could have reached escape velocity. Scale this up to collisions between larger protoplanets or between planets and massive impactors, and you can generate truly enormous ejection velocities. When two planetary scale bodies collide at tens of kilometers per second, the kinetic energy released is staggering, equivalent to millions or billions of nuclear weapons. Some fraction of the material from such collisions is vaporized, some melts, but some is ejected intact at velocities that can exceed the system's escape speed. These collision-ejected objects would have different characteristics than gravity-ejected ones. They might be fragments, pieces of larger bodies, rather than intact small worlds. They might be heated, partially melted, their surfaces modified by the intense energy of the impact. We don't have strong evidence that 3IATLAS is collision-ejected. Its cometary activity suggests it's a fairly typical icy body. But somewhere in the galaxy there are probably impact fragments wandering between the stars, carrying within them the scars of catastrophic collisions. The third mechanism is subtler, but potentially very important, especially for objects from the thick disk like 3IATLAS stellar encounters. Stars are not stationary. They're born in clusters often containing hundreds or thousands of stars packed into regions just a few light years across. During the early history of the Milky Way's thick disk, 4 to 10 billion years ago, star formation occurred in dense bursts, creating clusters that were even more crowded than typical modern star clusters. In these environments, close stellar encounters are common. When two stars pass within a few thousand astronomical units of each other, close by stellar standards, but still an enormous distance, their Oort clouds, or equivalent populations of distant comets, can be gravitationally disrupted. Objects that were loosely bound to one star can be stripped away, either captured by the other star, or if the geometry is right, flung into interstellar space. This mechanism is particularly relevant for thick disk objects, because the thick disk formed during this era of more violent stellar dynamics. The stars in the thick disk have higher random velocities, meaning stellar encounters were more energetic. And if 3IATLAS formed in a stellar cluster that has long since dispersed, which is likely since most stars are born in clusters that eventually evaporate, then a stellar encounter might have contributed to its ejection. Now you might be wondering, can we determine which of these mechanisms ejected 3IATLAS specifically? The honest answer is no, not with certainty. We don't know which star system it came from. That information is lost to billions of years of orbital perturbations. We don't know the configuration of planets in that system. We don't have witnesses to any collisions or stellar encounters. What we have is the end result, an object that has been traveling through interstellar space for 4.6 billion years, now passing through our solar system by chance. But we can make educated guesses based on statistics and what we know about planetary system formation. Gravitational ejection by giant planets is probably the most common mechanism overall, simply because every system with giant planets will undergo this process to some degree during formation. Collisions are more random depending on the specific architecture and dynamical history of each system. Stellar encounters are important in dense environments, but less so for isolated systems. What's remarkable is that all three mechanisms likely operate in every region of every galaxy where stars form. The result is a continuous production of interstellar objects, a galactic-scale phenomenon that has been occurring for billions of years. The thick disk where 3IATLAS originated was particularly productive because formation conditions there were more chaotic, with higher stellar densities and more violent dynamics. There's a common misconception worth addressing here. Some people imagine that interstellar objects must come from planetary systems that were somehow destroyed, that the presence of these wanderers implies catastrophe. But that's not accurate. Ejecting small bodies is a normal, even necessary part of planetary system formation. Our own solar system ejected countless objects and still formed stable planets. The objects that remain in the Kuiper Belt in the Oort cloud are only a small fraction of what originally existed. Most were either incorporated into planets or ejected. This is healthy, not catastrophic. It's how systems clean up their debris and settle into stable configurations. Another misconception is that interstellar objects are rare anomalies. As we've discussed, current estimates suggest trillions of such objects in the Milky Way alone. They vastly outnumber stars. The reason we've only detected 3 is purely observational. They're small, dark, and moving fast, making them extremely difficult to spot unless they pass very close to us. The Vera Rubin Observatory, now operational, is expected to dramatically increase the detection rate, potentially finding one interstellar object every few months instead of one every few years. Think about what this means for 3IATLAS's journey. After it was ejected from its home system 6 billion years ago, it has been on a ballistic trajectory modified only by gravitational encounters with other stars and large-scale galactic gravitational fields. It has never been recaptured. It has never found a new home. For billions of years, it has been falling through the galaxy, neither accelerating nor decelerating in any significant way, just coasting on the momentum it gained from that ancient ejection event. And here's something to ponder as you drift towards sleep. Every planetary system creates these exiles. Every system with giant planets goes through chaotic phases that send countless small bodies into eternal wandering. This means that the space between stars is populated with material from every generation of planetary systems from the oldest thick disk populations, like the one that produced 3IATLAS, to the youngest systems forming right now. These objects are witnesses to planetary formation processes spanning the entire history of the galaxy. Some of these wanderers will by pure chance eventually pass through other stellar systems as 3I-ATLAS is passing through Ors. A tiny fraction might even be captured if the encounter geometry is exactly right. And they happen to pass near a massive planet at just the right angle, though. Capture is far more difficult than ejection, and correspondingly rare. Most will wander forever, cooling slowly as cosmic radiation gradually processes their surfaces, carrying their frozen cargo of organic molecules and ices through the endless night. The physics of escape, the gravitational slingshots, the collisions the stellar encounters has created a kind of galactic mixing process. Material formed around stars in the thick disk can end up in the thin disk. Chemistry from ancient stellar systems gets distributed throughout the galaxy. And occasionally, very occasionally, one of these wanderers passes close enough to a young system with emerging intelligent life that it gets detected, studied, and appreciated for the cosmic time capsule it represents. But 3I-ATLAS isn't the first of its kind to pass through our solar system. And understanding what makes it unique requires comparing it carefully with those earlier visitors, with the enigmatic Oumuamua and the more familiar Borisov, because in their differences lies profound insight into the diversity of planetary systems across the galaxy. 3 visitors from beyond, 3 messengers from distant stellar systems, each arriving unannounced, each revealing something profound about the universe beyond our cosmic neighborhood. Yet, despite sharing the designation interstellar, these 3 objects could hardly be more different from one another. Oumuamua defied expectations with its bizarre asteroid-like appearance and mysterious acceleration. Borisov looked reassuringly normal, but harbored subtle chemical surprises. And 3I-ATLAS dwarfs them both in size and age, carrying secrets from an era when our galaxy was young. Understanding what makes each unique and what their differences tell us about the diversity of planetary systems across the galaxy requires us to examine them not in isolation, but as a collection, a small sample from which we can begin to draw conclusions about the billions of objects we haven't yet seen. The comparative study of these 3 interstellar objects represents one of the most exciting developments in modern astronomy, and if you're finding this cosmic detective story as fascinating as I do, I'd be honored if you take a moment to like this video and subscribe to the channel. Each subscriber helps us continue exploring these profound questions about our place in the universe. Now, let's examine what each of these visitors taught us. Let's begin with 1I Oumuamua because it was first and because it shattered our assumptions about what interstellar objects should look like. Discovered on October 19, 2017 by the Pan-STARRS telescope in Hawaii, Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, immediately puzzled astronomers. Its trajectory was clearly hyperbolic, confirming interstellar origin, but everything else about it was strange. First, there was its shape. As Oumuamua tumbled through space, its brightness varied dramatically, with a period of about 7.3 hours. This variation suggested it was highly elongated, either cigar-shaped or possibly pancake-shaped, though the cigar interpretation became more popular. The brightness changes implied a length-to-width ratio of at least 10:1, possibly even more extreme. Imagine an object perhaps 100 meters long, but only 10 meters wide. Nothing in our solar system looks quite like this. Our asteroids and comets tend to be more compact, closer to spherical, or only moderately elongated. Why would an interstellar object be so strangely shaped? Various theories emerged. Perhaps it was a fragment from a planetary collision, sheared into this elongated form by the violence of the impact. Perhaps it was a shard of a larger body that had been tidally disrupted during a close stellar encounter. Or perhaps, and this is where things got really interesting, it had been shaped by some process we don't fully understand, possibly even artificially. That last suggestion came primarily from Professor Avi Loeb at Harvard, who pointed out that we couldn't definitively rule out the possibility that Oumuamua was an artificial object, perhaps a light sail, a thin reflective surface pushed by starlight sent by some extraterrestrial civilization. This hypothesis generated enormous public interest and considerable scientific controversy. Most astronomers favored natural explanations, but Loeb correctly noted that we should consider all possibilities that fit the data, however unlikely they might seem. But the shape wasn't even the strangest thing about Oumuamua. As telescopes tracked it departing the solar system, astronomers noticed something unexpected. It was accelerating, moving faster than gravity alone could account for. This non-gravitational acceleration is actually common in comets. It's caused by the rocket effect of outgassing, where sublimating ices push the nucleus like a thruster. But Oumuamua showed no visible coma, no tail, no detectable outgassing of water vapor or other common volatiles. It looked like an asteroid, but was accelerating like a comet. The scientific community wrestled with this puzzle for years. If it wasn't water causing the acceleration, what was it? One leading hypothesis proposed that Oumuamua was composed largely of nitrogen ice similar to the surface of Pluto. Nitrogen ice sublimates at lower temperatures than water ice, and the sublimation produces nitrogen gas, which is transparent and wouldn't create a visible coma. This could explain both the lack of visible outgassing and the acceleration. The nitrogen ice hypothesis also suggested that Oumuamua might be a fragment of a Pluto-like world from another star system chipped off during a collision and sent wandering through space. Another hypothesis suggested that Oumuamua was outgassing hydrogen. Hydrogen is the lightest, most transparent gas, virtually undetectable with current instruments, but it could provide the necessary thrust. Where would the hydrogen come from? Laboratory experiments have shown that when water ice is bombarded by cosmic rays over millions of years in interstellar space, it can create molecular hydrogen trapped within the ice matrix. As the object approaches a star and warms slightly, this hydrogen could escape, providing acceleration without visible outgassing. The honest truth is that we don't know for certain. Oumuamua was discovered too late. It had already passed perihelion and was heading outbound when we spotted it. Astronomers had only 80 days to study it before it faded beyond detection. We never got a spectrum detailed enough to definitively identify its composition. We never saw it up close. And now, it's gone beyond the reach of even our most powerful telescopes, and it will never return. It remains one of astronomy's great mysteries, a puzzle that may never be fully solved. But Oumuamua taught us several crucial lessons. First, it demonstrated that interstellar objects exist and can be detected with current technology. Before 2017, these objects were purely theoretical. Oumuamua made them real. Second, it showed us that interstellar objects don't necessarily look like solar system objects. We can't simply assume that comets from other stars will look like our comets. The universe is more diverse than our imagination. Third, it sparked a revolution in preparedness. After Oumuamua, astronomers and mission planners began seriously discussing rapid response missions to intercept future interstellar visitors, knowing that we need to be ready when the next one arrives. Then came 2I Borisov, discovered on August 30th, 2019 by amateur astronomer Gennady Borisov. Using a 0.65-meter telescope he built himself. This discovery was remarkable not just for the object, but for the discoverer, proof that you don't need billion-dollar facilities to make profound contributions to astronomy. Borisov's amateur status makes his discovery one of the great romantic stories in modern science, a reminder that the spirit of discovery is accessible to anyone with dedication and clear skies. Unlike Oumuamua, Borisov looked immediately familiar. It had a coma, that characteristic fuzzy appearance of gas and dust surrounding the nucleus. It had a tail streaming away from the sun. It brightened as it approached perihelion and faded as it receded. In every visible respect, it looked like a normal comet from our own solar system. Scientists around the world breathed a collective sigh of relief, finally an interstellar visitor we could understand. But as observations accumulated, subtle differences emerged. When astronomers measured the polarization of light reflected from Borisov's coma, essentially how the dust particles scatter light in different directions, they found it was higher than typical solar system comets. The polarization characteristics suggested that Borisov's dust particles were either larger or compositionally different from what we normally see. This marked Borisov as unusual, even though its overall appearance was familiar. Spectroscopic observations revealed another surprise. Borisov was carbon monoxide rich and carbon chain depleted. It had high amounts of CO, but low amounts of molecular carbon C2 relative to cyanide. This placed it in a rare class sometimes called blue comets because of their spectroscopic properties. In our solar system, only a handful of comets show this characteristic, and they're thought to have formed in extremely cold regions, perhaps in zones analogous to or beyond the Kuiper Belt. The composition told a story Borisov likely formed in a very cold region of its parent planetary system, far from its home star, in conditions where carbon monoxide, which has an extremely low freezing point, remained abundant. The low temperature and high CO content suggested pristine preservation, a sample of material that had been frozen since shortly after its formation and had never been significantly heated until its passage through our solar system. But then something dramatic happened. In March 2020, observations from the Hubble Space Telescope revealed that Borisov's nucleus had fragmented. A piece had broken off, though the fragment represented only about 0.1% of the nucleus mass, a relatively small event. Cometary fragmentation isn't uncommon, especially for comets making their first passage close to the sun. The thermal stress of solar heating can crack the nucleus, releasing fragments. But witnessing this process in an interstellar comet provided valuable data about its structural properties. The nucleus size estimates for Borisov range from about 0.4 to 1.0 kilometers in diameter, significantly smaller than 3IATLAS, but still substantial. And here's an interesting point. Borisov's active outgassing made it much easier to detect than Oumuamua, despite being roughly similar in size or perhaps even smaller. The bright coma acts like a magnifying lens for detection purposes, which is why we tend to find active comets more readily than inactive asteroid-like objects. Borisov's visit lasted much longer than Oumuamua's. Astronomers tracked it for about 9 months before it faded from view in September 2020. This extended observation window allowed for much more detailed study. Multiple observatories captured spectra, measured its rotation, tracked its outgassing patterns, and watched the fragmentation event. Borisov became the best-studied interstellar object to date, at least until 3IATLAS arrived. Now, let's place these three objects side by side and see what patterns emerge. The size progression is striking. Oumuamua at roughly 100 meters, Borisov at 400 meters to 1 kilometer, and 3IATLAS at potentially 5 kilometers or more. That's a range of 3 to 6 orders of magnitude in volume, assuming 3IATLAS is on the larger end of the size estimates. This tells us immediately that interstellar objects span a wide range of sizes, from small fragments to substantial bodies that qualify as dwarf comets or even minor planets. The age progression is equally telling. Based on the trajectory analysis by Kokarov and Loeb, Oumuamua appears to be roughly 1 billion years old, originating from the thin disk of the Milky Way. Borisov is intermediate at approximately 1.7 billion years, also from the thin disk. 3IATLAS at 4.6 billion years from the thick disk is dramatically older. This age distribution suggests that interstellar objects are produced throughout galactic history, not just in recent epochs. Ancient planetary systems contributed to the interstellar population billions of years ago, and that population persists with new additions constantly being made by younger systems. The compositional diversity is perhaps most fascinating. If the nitrogen ice hypothesis is correct, Oumuamua represents icy worlds from the cold outer reaches of planetary systems similar to Pluto. Borisov represents carbon monoxide-rich carbon chain depleted comets from extremely cold formation zones. 3IATLAS represents methanol-rich organically complex objects from regions where prebiotic chemistry could flourish. 3 different chemical signatures, 3 different formation environments, 3 different types of planetary systems. What does this diversity tell us? It confirms what exoplanet studies have been showing. Every planetary system is unique. The architecture varies. Some have hot Jupiters, giant planets orbiting close to their stars. Some have systems of super-Earths, a planet type we don't have in our solar system. Some have eccentric giants that would destabilize the inner system. And each architecture produces its own characteristic population of small bodies with distinct compositions based on where and when they formed. There's an important lesson here about scientific expectations versus reality. Before Oumuamua, if you had asked astronomers what an interstellar comet would look like, most would have described something like Borisov, a normal-looking comet with a coma and tail chemically similar to our own comets, but perhaps with some interesting variations. Oumuamua taught us that our expectations can be badly wrong. The universe is under no obligation to conform to our assumptions. This has profound implications for how we approach future discoveries. When the Vera Rubin Observatory begins detecting interstellar objects regularly, potentially one every few months, we should expect continued surprises. Some might look like Borisov, reassuringly familiar. Some might resemble Oumuamua, strange and puzzling. Some might be completely different from anything we've seen before. The sample size of 3 is far too small to draw definitive conclusions about what's typical or normal. Consider the common mistakes that people make when thinking about these objects. One misconception is that Oumuamua must be artificial because it's unusual, but unusual doesn't mean artificial. Nature produces countless phenomena that seem strange until we understand them. Before we discovered pulsars, their precisely timed radio pulses seemed potentially artificial. They turned out to be rapidly spinning neutron stars, completely natural, but unlike anything we had imagined. Another misconception is that Borisov being normal makes it less interesting, but Borisov's value lies precisely in its familiarity. It provides a reference point, a known quantity against which we can measure other interstellar objects. It tells us that some planetary systems produce comets very similar to ours, which is itself an important data point about galactic-scale planetary formation. A third misconception is that these 3 objects represent the typical population. They don't. They represent what we can detect with current technology, which is biased toward larger, more active objects that pass relatively close to the sun. There's undoubtedly a vast population of smaller objects, inactive objects, objects on trajectories that don't bring them near any star bright enough to trigger outgassing. We're seeing the tip of the iceberg. Think about what would have happened if the order had been reversed if we had discovered Borisov, first then 3IATLAS and finally Oumuamua. We might have concluded that interstellar comets are basically like solar system comets just from other stars. Then Oumuamua would have completely upended that assumption. The order of discovery matters for shaping our expectations, but the reality is that all 3 are legitimate representatives of the interstellar population. Just different examples from a vast and diverse collection. As you settle into sleep tonight, consider this somewhere in the galaxy. Right now, an object is being ejected from its home system, beginning a journey that might last billions of years. Perhaps it will pass through our solar system in the distant future, when humanity has spread to other worlds, or perhaps vanished entirely. Perhaps it will pass through some other system, around some other star, detected by some other civilization, asking the same questions we're asking now. The galaxy is full of these wanderers, these cosmic time capsules, each one unique, each one carrying information about worlds we'll never see. And we're only just beginning to learn their stories. But 3IATLAS's story isn't complete without understanding the specifics of its passage through our solar system, the precise timing of its closest approaches, the safe distances involved, and where this ancient traveler is headed next, on its endless journey through the stars. Mark your calendar for December 19th, 2025. On this day, an object that has been traveling through the galaxy for 4.6 billion years will reach its closest point to Earth during its passage through our solar system at precisely 1.8 astronomical units, about 170 million miles or 270 million kilometers. 3IATLAS will sweep past our planet at 60 kilometers per second, a cosmic near miss that is paradoxically perfectly safe. This moment represents the culmination of months of anticipation, the point where observation conditions are optimal, where amateur astronomers with modest telescopes can glimpse this ancient wanderer for themselves, where professional instruments can capture their final detail measurements before 3IATLAS fades back into the darkness from which it came. But to truly appreciate this close approach, we need to trace the entire trajectory from discovery through perihelion to Earth passage and beyond, understanding not just where 3IATLAS is, but where it's been and where it's going. The journey of tracking an interstellar object through our solar system is a story of precision timing and the fundamental limitations of observation. So if you're captivated by these cosmic mechanics, I'd be grateful if you'd like this video and subscribe to the channel. Your support enables us to continue exploring these rare astronomical events in depth. Now, let's follow 3IATLAS through every stage of its solar system passage. When 3IATLAS was first detected on July the 1st, 2025, it was approximately 410 million miles from the Sun, about 670 million kilometers, or roughly 4.5 astronomical units. To put this in perspective, that's just inside Jupiter's orbit. Jupiter itself orbits at an average distance of 2 AU, so 3IATLAS was discovered in the outer solar system, still approaching, still accelerating as it fell toward the Sun's gravitational pull. At that distance, 3IATLAS was receiving only about 5% of the sunlight that Earth receives. It was cold, still mostly frozen though, beginning to warm. The discovery came at an ideal time early enough that astronomers would have months to plan observations late enough that the object was bright enough to detect. Had it been discovered just a few weeks later, precious observation time would have been lost. Had it been discovered much earlier, it would have been far fainter and harder to study. The timing, while fortuitous, also reflects the improving capabilities of survey telescopes like ATLAS, which scan the sky, methodically detecting ever fainter objects. From July through September, THRS, ATLAS continued its inward journey, growing gradually brighter as it approached the Sun. Astronomers tracked it carefully, refining the orbital calculations with each new observation. The trajectory was clear. 3IATLAS would reach perihelion, its closest approach to the Sun, on October 30th, 2025, at a distance of approximately 1.4 astronomical units, or about 130 million miles, 210 million kilometers. That's just inside the orbit of Mars, which averages 1.52 AU from the Sun. Think about what this perihelion distance means. 3IATLAS was never going to come particularly close to the Sun by cometary standards. Some comets from our own solar system pass within a few million miles of the Sun, diving deep into the solar corona. These sun-grazing comets experience extreme heating, often fragmenting or evaporating entirely. But 3IATLAS maintained a respectful distance, never venturing inside Earth's orbit, never approaching close enough to experience truly extreme heating. At perihelion, 3IATLAS was receiving about half the sunlight that Earth receives, enough to significantly warm its surface, triggering the sublimation of ices and creating the coma and tails that observers were documenting. The comet brightened noticeably as it approached this point, its activity increasing as more surface area warmed above the sublimation temperatures of water, ice, carbon dioxide, and other volatiles. But here's where the story gets particularly interesting. As October progressed and perihelion approached, 3IATLAS moved into a position where it was nearly directly behind the Sun as viewed from Earth. This solar conjunction, which we touched on earlier, created a blind spot lasting roughly 2 months. From late September through November, Earth-based telescopes couldn't observe 3IATLAS because pointing at it meant pointing too close to the Sun. The brilliant glare of our star, billions of times brighter than any comet, made observation impossible. This is where the Punch mission proved invaluable. Those 4 spacecraft specifically designed to observe the Sun's corona using coronagraphs that block the solar disk could see 3IATLAS throughout conjunction. They tracked it continuously as it passed through the zone, invisible to other observers, capturing data during the critical perihelion period when the comet's activity was at its peak. This continuous observation revealed how the solar wind, that stream of charged particles flowing outward from the Sun, interacted with 3IATLAS's ion tail, pushing it directly away from the Sun, creating spectacular structures visible only to Punch's instruments. During this hidden period, 3IATLAS's velocity reached its maximum. Pulled by the Sun's gravity as it fell inward, the comet accelerated from its discovery velocity of about 137,000 miles per hour to approximately 153,000 miles per hour at perihelion. That's an increase of 16,000 miles per hour, about 7 kilometers per second, entirely due to gravitational acceleration. After perihelion, as the comet climbed back out of the Sun's gravitational well, it began to decelerate, trading kinetic energy for potential energy, gradually slowing back toward its original interstellar velocity. Then, in early December, Atlas emerged from behind the Sun, reappearing in Earth's morning sky. Observers who had been waiting impatiently through the long conjunction finally had their chance again. And the comet had changed. Having passed through perihelion, having been heated to its maximum temperature, it showed evolved activity patterns. The coma, though still present, was different in structure. The tails recorded by JUICE and other spacecraft during conjunction were now observable from Earth as well. Amateur astronomers checking the ephemerides, the predicted positions found 3IATLAS in the constellation Leo, near the bright star Regulus. At magnitude 10.9 by mid-December, it was within reach of an 8-inch telescope under dark skies, though it remained a challenging target requiring some experience to locate and identify. It wasn't a spectacular naked-eye comet like Hale-Bopp or Neowise. It was subtle, faint, but observable for those who knew where to look and had the patience to find it. And then came December 19th, 2025, the closest approach to Earth. At 1.8 astronomical units, 3IATLAS passed at a distance of approximately 270 million kilometers. To visualize this, imagine that the Earth-Sun distance is about 150 million kilometers, 1 astronomical unit. 3IATLAS passed at 1.8 times that distance. It's like saying if the Earth-Sun distance is 1 block, 3IATLAS passed 1.8 blocks away. Close by cosmic standards, but absolutely safe. There was never any danger of collision, never any possibility of atmospheric entry or impact. Let me be very clear about this because there's often public concern when comets or asteroids make close approaches. The term close in astronomy is relative. When we say close, we mean close compared to interplanetary distances, not close in any threatening sense. An object at 1.8 AU is nearly twice as far from Earth as the Sun is. It's 700 times farther than the Moon. At that distance, 3I's Atlas couldn't possibly affect Earth. No gravitational influence, no debris risk, no danger whatsoever. The December 19th close approach was significant purely for observational reasons. At that distance, 3IATLAS was as close to Earth as it would get during its entire passage, which means it was as bright as it would appear in our sky. This was the optimal moment for amateur observations, for final professional measurements, for capturing the last detailed images before the comet continued its outward journey and gradually faded from view. Think about the geometry. 3IATLAS entered the inner solar system from the direction of the constellation Cassiopeia, near the border with Perseus. Its trajectory brought it past the Sun's far side relative to Earth, which is why we experienced that 2-month conjunction and then continued outward passing Earth's orbital distance in mid-December. After the close approach, the comet continued moving away from both the Sun and Earth, heading toward the outer solar system and eventually back into interstellar space. At the time of close approach, 3IATLAS was moving at approximately 60.3 kilometers per second relative to Earth. That's about 135,000 miles per hour, or 217,000 kilometers per hour, fast enough to cross the distance from Earth to the Moon in just 6.3 hours. Fast enough that even if you could launch a spacecraft today, catching up to 3IATLAS would require enormous amounts of fuel and years of flight time. This is why interstellar objects are such challenging targets. By the time we know they're here, they're already leaving. Now, let's look forward. Where is 3IATLAS going? After passing Earth, the comet continued outward, crossing Mars's orbital distance in early January 2026. Mars itself won't be near the crossing point, but had the timing been different, spacecraft orbiting Mars, the various rovers, orbiters, and landers might have captured images of 3IATLAS from a different vantage point. As it is, the comet will pass through that orbital region without any close planetary encounters. The next significant milestone comes in March 2026, when 3IATLAS is predicted to pass relatively near Jupiter, though near again means millions of kilometers. Jupiter is the giant of our solar system, containing more mass than all the other planets combined, and its gravitational influence extends far into space. When 3IATLAS passes by, Jupiter's gravity will pull on it, slightly altering its trajectory by a small but measurable amount. Astronomers will track this deflection carefully as it provides information about 3IATLAS's mass and confirms the accuracy of our orbital models. After the Jupiter passage, 3IATLAS will continue outward, crossing the orbits of Saturn, Uranus, and Neptune over the following years. By the time it reaches Neptune's orbital distance, about 30 AU from the Sun, it will be incredibly faint, detectable only by the most powerful telescopes, if at all. But even then, it will still be accelerating outward, still moving faster than the escape velocity of the solar system. Eventually, probably by late 2026 or early 2027, 3IATLAS will fade beyond the detection limits of even our largest telescopes. At that point, it will join the vast population of unobservable interstellar objects, those countless wanderers too faint and distant to see. But unlike most objects that fade from view, we'll know exactly where 3IATLAS is going. The orbital calculations are precise enough to project its trajectory centuries or even millennia into the future. 3IATLAS is heading toward the constellation Telescopium in the southern sky. This doesn't mean it's aimed at any particular star, and that constellations are just patterns we see from Earth, with stars at vastly different distances. But it tells us the direction of departure. As 3IATLAS leaves the solar system, it will gradually return to the interstellar velocity it had when it entered, roughly 60 kilometers per second relative to the local standard of rest. At that speed, it will take approximately 19,000 years to travel 1 light year. Let's put this in perspective. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. At 3IATLAS's speed, the journey would take roughly 80,000 years. And Proxima Centauri isn't even in the direction 3IATLAS is traveling. The comet is heading in a different direction entirely toward regions of space where the nearest stars are likely even farther away. It could be hundreds of thousands of years before 3IATLAS passes anywhere near another stellar system. And here's the profound reality: 3IATLAS will never return. Its trajectory is hyperbolic, not elliptical. It's not bound to our sun. After it leaves, it will continue on its journey through the galaxy, indefinitely cooling back to the frigid temperatures of interstellar space. The ices that sublimated during its passage through the inner solar system, refreezing if any, remain the coma and tails dissipating into nothingness. It will become once again a dark, frozen mountain of ice and rock, invisible, silent, carrying its cargo of ancient organic molecules through the endless night. Think about what this means for the concept of home. 3IATLAS left its birth system 6 billion years ago. It has no home star, no parent system to which it can return. It has been homeless for essentially the entire age of our solar system, and it will remain homeless for billions of years into the future. It will outlive our sun, which will exhaust its hydrogen fuel and expand into a red giant in about 5 billion years. It will outlive our solar system entirely, witnessing the death of everything we know while it continues its endless wandering. Yet during its brief passage through our solar system, from discovery in July 2025 to its fade from view, probably in late 2026, this homeless wanderer gave us an extraordinary gift. It gave us data about the early galaxy. It gave us insights into planetary formation processes in the thick disk. It gave us spectroscopic signatures of organic chemistry from 4.6 billion years ago. It gave us experience observing and tracking interstellar objects. And it gave us a profound reminder that we are part of a galaxy filled with such objects, each one a potential messenger from distant worlds. The December 19th close approach happening, as many of you listen to this, marks a special moment. It's the point where 3IATLAS comes nearest to our world, the moment of closest connection between our planetary system and this ancient visitor. For a brief time in cosmic terms, our trajectories align. Earth and 3IATLAS share the same region of space, separated by only 1.8 AU, close enough that photons from the sun bounce off the comet and reach our telescopes just 15 minutes later. It's a fleeting connection, but it's real. And when 3IATLAS continues on its journey, fading into the darkness, it carries with it a tiny piece of our moment in time, the electromagnetic radiation that bounced off it. While it was here, photons that will continue spreading outward, carrying a faint signature of the year 2025, long after human civilization has become history. But this close approach isn't just an ending, it's part of a larger story about how we detect these visitors and what the future holds as our technology continues to improve, because the revolution in interstellar object astronomy is just beginning. Imagine a telescope so powerful, so sophisticated, that it can photograph the entire visible sky every 3 nights, detecting objects 100 million times fainter than what your eyes can see. Imagine a data processing system so advanced that it can identify moving objects, classify them, and alert astronomers worldwide all automatically in near real time. This isn't science fiction. This is the Vera C. Rubin Observatory, now operational on Cerro Pachón in Chile, and it's about to transform interstellar object astronomy from a field of rare exciting discoveries into something approaching routine science. In the decade before Rubin, we found 3 interstellar objects. In the decade after Rubin becomes fully operational, we may find hundreds. And this revolution in detection capability isn't just about collecting more data. It's about fundamentally changing what questions we can ask about the galaxy, about planetary systems beyond our own. and about the invisible population of wanderers that fills the space between the stars. The coming transformation in how we study interstellar objects represents one of the most exciting developments in astronomy. And if you're as captivated by this revolution as I am, I'd be grateful if you'd like this video and subscribe. Every subscription helps us continue documenting these pivotal moments in scientific history. Now, let's explore what the Rubin Observatory will reveal. To understand why the Rubin Observatory is such a game changer, we need to first appreciate the limitations that have constrained interstellar object astronomy until now. Before Oumuamua's discovery in 2017, we had never detected an interstellar object passing through our solar system. Not one. This wasn't because they didn't exist. Theoretical calculations predicted they should be common, but because we simply weren't looking in the right way with sufficient sensitivity. Survey telescopes like Pan-STARRS, which discovered Oumuamua, and ATLAS, which discovered 3IATLAS scan portions of the sky, regularly looking for anything that moves or changes. They're designed primarily for planetary defense, finding asteroids that might threaten Earth, but they also discover comets, variable stars, supernovae, and occasionally interstellar visitors. But these surveys have limitations. They cover only portions of the sky, not all of it. They have detection thresholds. Objects fainter than a certain magnitude simply don't register. And they revisit each patch of sky on timescales of days or weeks, which means fast-moving objects might slip through undetected. The result is that our current detection rate for interstellar objects is roughly 1 every 3 to 5 years. Oumuamua in 2017, Borisov in 2019, 3IATLAS in 2025. That's 3 objects in 8 years, giving us a rate of about 0.4 detections per year. This is valuable. These 3 objects have taught us enormous amounts, but it's a tiny sample from which to draw conclusions about the broader population. Now consider what the Rubin Observatory brings to the table. Its primary mirror is 8.4 meters in diameter. That's 20.6 feet across, large enough to gather tremendous amounts of light. But size alone isn't what makes Rubin special. What makes it revolutionary is its field of view. Most large telescopes see a very small patch of sky at high resolution, perhaps the size of the full moon, or even smaller. Rubin sees 9.6 square degrees in a single image that's equivalent to about 40 full moons arranged in a rectangle. This enormous field of view, combined with its large mirror, means Rubin can survey vast areas of sky quickly while still detecting very faint objects. The survey strategy is called the Legacy Survey of Space and Time, or LSST. Over 10 years, Rubin will photograph the entire visible sky, about 18,000 square degrees, repeatedly creating a movie of the changing universe. Each patch of sky will be visited roughly every 3 to 4 nights, weather permitting. Over the decade-long survey, Rubin will capture millions of images, creating a data set so vast that it will enable research on virtually every topic in astronomy, from asteroids in our solar system to the most distant galaxies in the universe. For interstellar object detection, this systematic, comprehensive approach is transformative. Instead of surveying parts of the sky occasionally, we'll be surveying all of it regularly. Instead of detecting only the brightest interstellar objects, we'll detect fainter ones. Instead of discovering them late, often when they're already heading outbound, we'll catch many of them earlier when they're still inbound, giving us more time to plan observations. Astronomers have run simulations to predict Rubin's detection rate. The estimates vary depending on assumptions about the true population of interstellar objects, how many there are, what size distribution they follow, what their typical velocities are. But most predictions converge on roughly 1 detection every few months. That's a factor of 10 to 20 increase over current rates. Instead of 3 objects per decade, we might find 30 or more. Think about what this means for the science. With 3 objects, we can barely begin to characterize the population. We can note that they're diverse. That's clear from Oumuamua Borisov and 3IATLAS being so different from one another, but we can't say what's typical or rare. Are most interstellar objects like Borisov cometary and familiar? Was Oumuamua an outlier, or are strange asteroid-like interstellar objects common? How many are as large as 3I Atlas? How many are smaller? With 30 objects, we can start to answer these questions. We can construct histograms of size distributions, velocity distributions, compositional types. We can look for correlations. Do larger objects tend to be older? Do objects from certain galactic directions show different chemistry? We can compare the interstellar population with populations of comets and asteroids from our own solar system, identifying what's universal about planetary formation and what's unique to specific systems. With hundreds of objects, and that's what we might have, after a few decades of Rubin operations, plus data from future even more advanced surveys, we'll have enough statistics to make definitive statements. We'll know what the typical interstellar object looks like. We'll understand the range of variation. We'll be able to test theories about planetary system formation on a galactic scale using interstellar objects as our sample set. But Rubin's impact goes beyond just finding more objects. It will also find them earlier and track them better. Consider Oumuamua. It was discovered on October 19, 2017, but it passed perihelion back on September 9th, more than a month earlier. We found it on its way out. We never saw it at its brightest, never observed it at maximum activity. We had only 80 days to study it before it faded beyond detection. If Rubin had been operational in 2017, there's a good chance Oumuamua would have been discovered earlier, perhaps even before perihelion, giving us more time and better observation conditions. Early detection is crucial because it enables responsive observations. When an interstellar object is discovered with months of prime observation, time-remaining proposals can be written. Telescope time can be allocated. Space missions can potentially be redirected to observe from different vantage points. With Oumuamua, everything was rushed. With 3IATLAS, we had more time, and the resulting science has been much richer as a result. Rubin will give us that precious gift of time for many more objects. There's also the question of what Rubin will reveal about the distribution of interstellar objects in space. Right now, we don't know if they arrive uniformly from all directions, or if there's an anisotropy, a preferred direction. Theoretical work by Amir Siraj and Avi Loeb at Harvard predicts that there should be a detectable anisotropy due to the sun's motion through the local standard of rest. The sun is moving at about 230 kilometers per second around the galactic center, and this motion means we're constantly running into interstellar objects coming from certain directions more than others, much like how driving through rain makes it seem like the rain is coming more from the direction you're heading than from behind. Detecting this anisotropy requires a large sample. You can't see a pattern with just 3 data points. But with 30 or 50 objects, the pattern should emerge clearly. And if it does, that will confirm our understanding of galactic dynamics and the sun's motion through the galaxy. If the pattern doesn't appear, or appears differently than predicted, that would be equally interesting, suggesting something unexpected about the interstellar object population or the structure of the local neighborhood. Rubin will also help address one of the key questions in interstellar object science. What is the characteristic ejection velocity? When objects are flung out of planetary systems, they receive a range of velocities depending on the specifics of the ejection event. Some barely escape, moving only slightly faster than escape velocity. Others are ejected violently, moving at many times escape velocity. The distribution of ejection velocities tells us about the dynamics of planetary system formation, about how chaotic the early epochs are, about the efficiency of gravitational scattering, about the typical energy budgets of ejection events. Right now, with only 3 objects, we can't constrain this distribution. But as Rubin builds up a catalog, we'll be able to plot the velocity distribution and compare it with theoretical predictions. this seemingly technical detail actually reveals fundamental information about how planetary systems form and evolve. Now, here's where things get really exciting. Rubin's discoveries will enable rapid response missions. This is something that has been discussed extensively in the scientific community since Oumuamua. Several groups have published feasibility studies showing that with current or near-future propulsion technology, it's possible to launch a spacecraft to intercept an interstellar object, at least if we detect it early enough, and if its trajectory passes relatively close to Earth. One study published by researchers at the Initiative for Interstellar Studies concluded that launching a flyby mission to an interstellar object is feasible and affordable. With chemical propulsion, no exotic technologies required. The key requirements are early detection, ideally months or years before perihelion, and a favorable trajectory. The spacecraft would use a gravity assist from Jupiter or another planet to build up speed, then intercept the interstellar object as it passes through the inner solar system, capturing close-up images, spectra, and perhaps even physical samples if the mission design allows for it. Imagine what such a mission could reveal. Instead of observing 3IATLAS from 170 million miles away through telescopes, imagine a spacecraft passing within a few hundred kilometers, capturing images with resolution measured in meters per pixel instead of thousands of kilometers per pixel. Imagine spectrometers analyzing the composition directly without the atmospheric interference that ground-based observations must contend with. Imagine possibly even a sample return mission bringing back pristine material from an interstellar visitor, material we could analyze in laboratories with techniques impossible to apply from a distance. This isn't idle speculation. NASA and ESA have both commissioned studies on interstellar object intercept missions. The technology exists. What's been missing is the target catalog, knowing far enough in advance that an interesting object is coming, so there's time to plan and launch a mission. Rubin will provide that catalog. And when the next truly exceptional interstellar object is detected, perhaps something even more unusual than Oumuamua, perhaps something large enough, and on a trajectory favorable enough to make an intercept mission irresistible, there's a real possibility that we'll go from remote observation to direct exploration. But let's be realistic about the challenges. Not every interstellar object Rubin finds will be a good mission target. Many will be on trajectories that are unfavorable, passing too far from Earth, or moving too fast for an intercept to be practical with available propulsion systems. Many will be discovered too late for a mission to be mounted. Some will be too faint or scientifically uninteresting to justify the hundreds of millions of dollars a space mission requires. But out of 30 or 50 or 100 objects detected over the coming decades, surely a few will be exceptional, large, close passing detected, early, compositionally unique, and those will be candidates for missions. The economic argument for these missions is surprisingly strong. Yes, they're expensive, perhaps $300 million to $500 million for a New Horizons class flyby mission. But compare that to the scientific return. Every interstellar object represents material from another stellar system, potentially billions of years old, carrying information about planetary formation, processes we can access no other way. The cost per bit of information is actually quite favorable compared to missions to bodies in our own solar system. There's a common misconception that needs addressing. Some people imagine that the increase in detection rate means the number of interstellar objects passing through our solar system is increasing. That's not the case. The number passing through is constant. It's always been roughly one object within Neptune's orbit at any given time, and that's been true for billions of years. What's changing is our ability to detect them. It's like saying that installing security cameras in a forest doesn't increase the number of animals living there, it just means you finally see them. Another misconception is that detecting more interstellar objects means they're somehow dangerous. But remember, these objects have been passing through our solar system for all of Earth's history. They pass at safe distances. Typical closest approaches are measured in astronomical units, not in thousands of kilometers. The increase in detection doesn't change the risk. It only changes our awareness. And that awareness is purely beneficial, expanding our understanding of the cosmos without introducing any new hazards. As you settle deeper into rest, tonight consider the trajectory we're on. In 2017, we found our first interstellar object, Oumuamua, and the discovery electrified the astronomical community. In 2019, we found Borisov confirming that these objects are regularly detectable. In 2025, we found 3IATLAS, the oldest and largest yet. And now, with Rubin operational, we're entering an era where interstellar objects transition from headline-making discoveries to regular features of astronomical research. Within a decade, there will be enough data to write textbooks on interstellar object populations. Within 2 decades, we might have sent spacecraft to study them up close. Within our lifetimes, these visitors from other stars will become familiar. Their properties catalog their origins, trace their chemical signatures, decoded into stories of worlds we'll never see, but can finally begin to understand. And as this revolution unfolds, transforming how we study the galaxy and our place within it, we must remember that every discovery, every new object in the catalog, every data point in the distribution represents not just a scientific measurement, but a connection to the vast cosmic ecosystem of which we're a part. And that connection carries implications that extend far beyond astronomy into the very question of what it means to be a civilization, capable of recognizing these ancient messengers and learning from them. We've traveled far together tonight, across billions of years, through countless light years of space, following the journey of an object so ancient that it witnessed the formation of our own solar system. From the outside, a silent observer carrying within it the chemical fingerprints of a world that may no longer exist. 3IATLAS arrived at our cosmic doorstep, not by design, but by pure chance. And yet its passage has fundamentally altered how we understand our place in the galaxy. But the story of this ancient wanderer isn't just about one object, one discovery, one moment in time. It's about what happens when a civilization reaches the point where it can recognize these messengers, decode their secrets, and understand what they reveal about the universe. It's about the profound implications of knowing truly. Knowing that we're part of a galactic ecosystem filled with material from countless other worlds, each one a potential teacher, each one carrying lessons about cosmic history, planetary formation, the chemistry of life, and the deep patterns that shape galaxies over billions of years. Professor Avi Loeb, who has been studying interstellar objects since before Oumuamua's discovery, identified 6 revolutionary dimensions through which these visitors can transform our understanding of the cosmos. Let's explore each one, because together they paint a picture of why 3IATLAS and its interstellar siblings represent not just interesting curiosities, but genuine paradigm shifts in how we do astronomy. The first dimension is galactic dynamics. For centuries, astronomy has been primarily an observational science conducted at a distance. We look at stars through telescopes, we measure their spectra, we calculate their distances and motions, we build models of how galaxies work, but we can't touch them, we can't sample them directly. Interstellar objects change this fundamental limitation. When 3IATLAS passes through our solar system, it brings with it dynamical information, its velocity, its trajectory, its orbital eccentricity, that reveals how objects move through the galaxy on timescales of billions of years. The trajectory analysis performed by Kokharov and Loeb, tracing 3IATLAS backward through time, demonstrated that we can use these objects as probes of galactic structure. The vertical excursion from the galactic plane told us this object came from the thick disk. The velocity dispersion told us its approximate age. This isn't just academic, it means that as we build up a catalog of interstellar objects, we're essentially creating a map of the galaxy's dynamical history, traced through physical samples rather than just photons. We're touching the galaxy, not just looking at it. The second dimension is exoplanet chemistry. When astronomers discover planets around other stars using techniques like the transit method or radial velocity, they can sometimes obtain spectra of those planets' atmospheres, revealing their chemical composition. But there are limits to what spectroscopy can tell us from hundreds of light years away. Small molecules are hard to detect. Surface composition is nearly impossible to measure for rocky planets. We get glimpses, not complete pictures. Interstellar objects provide ground truth. The methanol to hydrogen cyanide ratio in 3IATLAS tells us something definitive about the chemistry of the protoplanetary disk, where it formed 4.6 billion years ago. That's information we could never obtain through spectroscopy of a distant exoplanet. As we catalog more interstellar objects and characterize their compositions, we're building a library of exoplanetary chemistry, actual samples from other planetary systems that we can compare with our theoretical models and our spectroscopic observations. This ground truth is invaluable for validating or refuting our assumptions about how planetary systems form and what conditions exist in protoplanetary disks across the galaxy. The third dimension is astrobiology, and this is where things become truly profound. The discovery that 3IATLAS carries high concentrations of methanol, a key precursor to more complex organic molecules, confirms that the building blocks of life form readily in planetary systems throughout the galaxy. This isn't speculation, we've measured it. We've detected these molecules in an object that formed 6 billion years ago around a different star in a completely independent stellar system. This has implications for the panspermia hypothesis, not in the science fiction sense of actual living organisms traveling between stars, but in the more subtle sense that the chemical raw materials for life might be distributed galactically. Every planetary system ejects material during its formation. That material wanders through interstellar space, occasionally encountering other systems. Over billions of years, this creates a kind of chemical mixing on galactic scales. Material from the thick disk, like 3IATLAS, can end up in the thin disk. Ancient chemistry can influence young systems. The galaxy becomes, in a sense, chemically connected. Does this mean life is common? We still don't know. The leap from organic molecules to actual living organisms is enormous, potentially requiring very specific conditions that might be rare. But what 3IATLAS tells us definitively is that the ingredients are there. The chemistry of life isn't a unique accident that happened only in our solar system. It's a widespread consequence of how carbon-based chemistry works in the cold environments of protoplanetary disks. And that's a profound realization. The fourth dimension is understanding the interstellar medium itself, the diffuse gas and dust that fills the space between stars. Interstellar objects travel through this medium for millions or billions of years, and the effects are visible in their properties. The radiation-hardened crust that cosmic rays create, the modification of surface chemistry by exposure to ultraviolet light from distant stars, the slow erosion from collisions with interstellar gas molecules and dust grains. By studying objects like 3IATLAS that have spent billions of years in interstellar space, we learn about the conditions in that space, the radiation environment, the particle densities, the chemical processes that occur over cosmological timescales. The fifth dimension is the potential for sample return. Right now, we observe interstellar objects from a distance using telescopes to capture their light and infer their properties. But as we discussed in the previous section, there's a realistic possibility that within the next few decades, we'll send spacecraft to intercept an interstellar object and either fly by it at close range or potentially even return samples to Earth. Imagine holding in your hand, or rather in a carefully controlled laboratory environment, a piece of another star system. Material that formed billions of years ago, billions of miles from here, around a star we may never identify. Material that has traveled through the galaxy longer than Earth has existed. This would transform interstellar object science from remote sensing to laboratory analysis. Instead of inferring composition from spectral lines, we could use mass spectrometry, electron microscopy, isotopic analysis, all the techniques that make meteorite studies so valuable. We could determine precise ages through radioactive dating. We could search for amino acids, for complex organics, for evidence of chemistry we didn't expect. This transition from remote astronomy to direct sample analysis would be comparable to the difference between looking at the moon through a telescope and actually holding a moon rock that Apollo astronauts brought back. The sixth dimension is technological inspiration. Throughout history, astronomical observations have driven technological development. The desire to see fainter objects led to larger telescopes. The need to process vast amounts of data drove innovations in computing. The challenges of space exploration pushed the boundaries of propulsion, materials, science, and systems engineering. Interstellar objects present new challenges that will drive new innovations. How do you detect objects moving at 50 kilometers per second? How do you design a mission to intercept something that will only be in range for a brief window? How do you analyze data from observations spanning dozens of instruments across space and ground-based platforms? These challenges inspire solutions that often find applications far beyond their original purpose. The image processing algorithms developed to enhance faint comet observations get used in medical imaging. The orbital calculation software becomes useful for satellite constellation management. The rapid response protocols for interstellar object discovery inform planetary defense strategies. Science and technology advance together, each pushing the other forward. But beyond these six dimensions lies something even more fundamental: what 3IATLAS and its interstellar siblings teach us about cosmic time. Think about the fact that this object has been traveling through the galaxy for 4.6 billion years. When it was ejected from its home system, Earth was just forming. The solar nebula was still collapsing. The proto-sun was just beginning to ignite fusion. The giant planets were gathering mass from the surrounding disk. Everything we know, every mountain on Earth, every ocean, every fossil, every civilization, all of it has come into existence during 3IATLAS's journey. And when 3IATLAS finally leaves our solar system, continuing its wandering through the galaxy, it will outlast everything in our system. Our sun will exhaust its hydrogen fuel in about 5 billion years, swelling into a red giant that will eventually engulf the inner planets. The outer planets will be pushed into more distant orbits. Eventually, the sun will shed its outer layers, leaving behind a white dwarf that will slowly cool over trillions of years. And through all of that, 3IATLAS will still be traveling, still carrying its cargo of 4.6 billion-year-old organic molecules, still bearing witness to the galaxy's evolution. This perspective on time is humbling. It reminds us that our moment in cosmic history, this brief period when humans exist, when we have technology capable of detecting these visitors, when we can study them and learn from them, is infinitesimally small compared to the timescales on which interstellar objects operate. We're catching glimpses of processes that span billions of years, and we should feel extraordinarily fortunate to be alive during this particular century when such observations became possible. There's also a deeper philosophical implication. The existence of interstellar objects, billions of them wandering through the galaxy, each one carrying material from a different planetary system, each one potentially harboring organic molecules, each one a time capsule from some distant era, suggests a kind of cosmic connectedness that transcends the vast distances between stars. We tend to think of stellar systems as isolated, separated by light years of empty space evolving independently. But the continuous ejection and wandering of objects like 3IATLAS means that material cycles through the galaxy on timescales of billions of years. Ancient thick disk chemistry ends up in young thin disk systems. Material ejected from one star system eventually passes through others. The galaxy is not a collection of isolated systems, but a connected web linked by these wandering messengers. And here's something to ponder: if interstellar objects regularly pass through stellar systems, and if some tiny fraction of them are captured rather than passing through, then Earth itself might contain interstellar material. Not just the atoms and molecules that were present in the solar nebula from which our system formed, though those too are made of material from previous generations of stars, but actual chunks of rock or ice that were captured from interstellar objects during Earth's early history. We might be walking on ground that contains fragments from other star systems mixed in with native material, indistinguishable without detailed isotopic analysis. This is speculative. We have no confirmed samples of interstellar material in Earth's geological record, but it's plausible. And if true, it means that studying Earth's ancient rocks isn't just studying our planet's history. It's potentially studying the history of other worlds, other systems, other epochs of galactic evolution. Every rock could be a messenger if only we knew how to read its message. The discovery of 3IATLAS, and before it, Oumuamua and Borisov, marks a transition point in human history. For thousands of years, humans looked at the stars and wondered what was out there. For centuries, we've had telescopes powerful enough to study other worlds in detail. For decades, we've understood the physics of how planetary systems form. But only in the last 8 years have we actually detected and studied objects from other stellar systems. We've crossed a threshold. We're no longer purely observational astronomers studying distant phenomena. We're beginning to sample the galaxy, directly touching material from beyond our solar system, learning from it, incorporating it into our models of how the universe works. And this is just the beginning. The Vera Rubin Observatory is now operational. Future telescopes even more powerful are being planned. Detection rates will increase. More interstellar objects will be discovered. Some will be similar to the 3 we've already seen. Others will undoubtedly surprise us, revealing properties or behaviors we didn't anticipate. And eventually, if we're wise and fortunate, we'll send missions to study them up, close, bringing back samples, transforming astronomy into a hands-on science in ways we're only beginning to imagine. What would Gennady Borisov, the amateur astronomer who discovered 2I Borisov from his backyard observatory in Crimea, tell you about the accessibility of this science, that you don't need billion-dollar facilities to make profound contributions? What would the hundreds of astronomers who collaborated on studying 3IATLAS tell you about the importance of teamwork? That great discoveries require not just individual brilliance, but collective effort. What would the ancient wanderer itself tell you if it could speak? Perhaps simply this: the universe is larger, older, more connected, and more generous with its lessons than we often realize. We need only pay attention, remain curious, and stay humble in the face of the cosmos's vast mysteries. As 3IATLAS continues its journey outward, fading from our telescopes, disappearing back into the darkness from which it came, it leaves behind something precious: knowledge. Knowledge about galactic history, about planetary formation, about organic chemistry, about cosmic timescales, about the processes that shape worlds across billions of years and billions of miles. That knowledge becomes part of humanity's collective understanding, woven into textbooks, incorporated into models, inspiring future research, perhaps even guiding future missions to other interstellar visitors. And somewhere in the galaxy right now, another object is being ejected from another planetary system, beginning its own billions of years journey through the darkness. Perhaps it will pass through our solar system, millennia or millions of years from now, when humanity has spread to other worlds or perhaps vanished entirely. Perhaps it will pass through some other system, around some other star, detected by some other civilization, asking the same questions we're asking tonight. The galaxy continues its ancient cycles, indifferent to our presence, but generous with its lessons for those willing to look up, to wonder, and to learn. Thank you for joining me on this journey through space and time, following the path of 3IATLAS, from its ancient origin in the thick disk of the Milky Way through 4.6 billion years of wandering to its brief passage through our solar system, and its eventual fade back into interstellar darkness. I hope these stories from the cosmos bring you not just knowledge, but also a sense of wonder, a feeling of connection to something larger than ourselves, and perhaps a more peaceful transition into sleep, knowing that we're part of this vast, ancient, endlessly fascinating universe. If you enjoyed this exploration, please consider subscribing to the channel and staying connected for future journeys through the cosmos. There are so many more stories to tell, from the formation of the first galaxies to the intricate dance of binary stars, from the violent beauty of supernovae to the gentle patience of planetary formation. Each story reveals something profound about the universe and our place within it. Until we meet again under the stars, rest well, dream peacefully, and remember, we are all made of stardust, connected to the cosmos in ways both beautiful and profound. Good night and clear skies.